Good. We're going to get started. Welcome to the second workshop on generative models for computer vision. Last year's workshop was actually highly successful, so we thought, why not do it again? And judging from the crowd that is here and the 45, 50 people that are online, seems to be a lot of interest, so that's good. Let me first thank the organizers here for helping us to set this up. Our seniors for giving very valuable advice. And then Pangneng helping me to organize this, also taking care of the website, Lingo, actually taking care of the invitations of the seniors, of many of the seniors. And then the two Michaels who actually did a tremendous job in helping me with the reviews, which was actually a lot of work this year because we had many submissions, unexpectedly many submissions. So yep, thanks to everyone. And of course, why is this slide not showing? Sorry, I need to show the slide because it's so important. Yeah. It is here. Yeah. Let me also share the screen again. Thanks a lot to all of the people who helped us review as well. This was, as I said, yeah, lots of work. We had like, I think around 70, 80 papers. I don't remember anymore exactly. Short papers, long papers. So, yep, thanks to everyone for reviewing. I thought a little bit about also putting up a list of all of the reviewers who didn't do their job. You know, this sounds a little funny, but I think, you know, even on this rather small scale, you know, it actually created a lot of issues. And at the scale of CVPR, you know, I think, as I heard in the area chair meeting, we have this at a much, much larger scale. So I think our community kind of needs to think about how to resolve this. And I'm a big fan of public shaming. I haven't done this here, but yeah, maybe next year. Let's see, you know, like it would be actually interesting to discuss this with some of you over the coffee breaks. Yeah, so, but thanks a lot to everyone who actually did their job very well. Yeah, so let me give a little bit of a motivation of why we are here and why we are organizing this workshop. I mean, we've seen a lot of progress, even like compared to last year, right? If you would compare the current state to exactly the state that we had last year at this time, it's like amazing to see what actually happened on the way, right? I mean, for example, single view reconstruction, but also video generation. I mean, it's crazy what we can do right now. And so this, like, you know, we've seen purely learning-based models doing a crazy good job. And then on the other side, we've actually also had a lot of advances in like really fully controlled 3D synthesis, right, with a lot of inductive bias. So really like mostly on the other spectrum of image generation, right, full control over, you know, human avatars, so 3D faces, right, even combination with semantic fields. So we have like a lot of advances in the full spectrum of generative modeling. And the question that arises with this is, how does this now relate to classical, what we could call like classical computer vision, so semantic understanding of the real world, right? So we have these like kind of classical tasks, some of them obviously outdated, right? But you know, where's this intersection between generative modeling, predicting the next frame, and understanding, right? In order to elaborate on this question, we've invited 8 experts today to give their view on this, where they are in the spectrum of fully learning, fully 3D inductive biases. I hope to see a lot of interesting discussions here. And we also have 40 posters, which is like, I think, double as much as we had last year. Let's see if we can continue this exponential growth over the years. For those of you who are interested, like I hope every one of you is interested, and for those of you who are presenting, so the poster session is actually not in this building, right? It's in the ARC building over there, which means it's 15 minutes, 10, 15 minutes. It's in the top floor, right? Yeah, I was not aware of this, so there is, you know, a little bit of effort that you have to do in order to get to the poster session. We have the poster boards 1 to 40, so make sure to go there. This is short papers, long papers. The short papers are actually mostly papers that are presented here at CVPR on generative models, right? So I think what this will evolve to is to be like some form of smaller venue, focused venue for generative modeling, where actually people who publish at the main conference in the context of generative models can actually present their posters in a sense twice, right? Once for a focused community and then for the general community at the main conference. So I hope this will evolve in this direction. So for those of you who present posters, please set this up during the session, hang it up during the session, and then take it down afterwards again so that no one has to clean up after. And because we need to walk over there 15 minutes and then come back 15 minutes, we've extended the poster session by half an hour, meaning that it starts at 12:30 and it ends at around 2 p.m. So 2 p.m. we'll start here again. This gives you enough time to talk and to discuss about your work, right? So meaning you can, after 12, when the last session, the last morning session, you can go down, get your lunchbox, and then walk over and have discussions over lunch, and then come back here at 2. Good, so that's the schedule of today. We're going to end the opening soon. And then we have Gianluca and CU presenting. We have a short coffee break, and then signing and Alan closing the morning session. We'll have this 2-hour lunch break, which you should mostly use also for discussions at the posters. And then we have Jajun and Katerina, coffee break, and we'll close with Andrea and Federico. So 8 top talks. Super excited to see this. And then we'll have like short closing and yeah. So, and with this, we have still 5 minutes to go. And I think we should actually start on time rather than, so we'll have like a short break of 4 minutes. Gianluca can set up and then I'll introduce him and we'll start on time at 9. Something to drink here and just. So I will some point wait. So yeah, I will let you know like yeah, but you're looking in this direction. Yeah, that is right. Okay. Yeah, but in worst case, I will just briefly say, and then yeah, I guess we'll have. Like the room, it was like 10 minutes ago, they were already finished. Person had like 80 or so. Let me check. Ah, no. Ah. Right? Yeah. We can. I could.
Muted now.
Okay. Good. All right. Test. No, does not work. Oh, fantastic. Test. Not. Test. Not working. How do we do this now? I mean, either you need to shout. I mean, it was
We can hear you very well online.
Yeah.
I go and get someone else. You need to shout.
Okay.
But online it works, right? But you know, I mean, here it doesn't. Test. Well, I'll go and get someone and then
Let me check if it's
just to make sure.
Yeah. I'm not sure. I think it's. I think it's selected my MacBook Pro microphone, maybe.
No, but I mean, you know, here you're not. Now it works. Can you hear me on the mic? No, right. Well, anyway. I think we're just going to start that. there's no way I will find out what this is.
Okay, I can just,
Yeah, I think we
shout.
just shout.
I'll shout if you.
Okay. Test. Yeah. So, I mean, we had issues with the microphones also yesterday in the workshop, so this can go on and off. I hope we're going to fix this afterwards. But yeah, I mean, we're going to shout now for the first talk, I guess. I'm super happy to have Gianluca Corrado here with us. Actually, the principal scientist at Wave. I think the autonomous driving company in the UK for sure, in the world as well. Super happy to have him here, the team lead or the of the Gaia project, right? So I think it is in some sense, really pioneering work that showed what is possible in terms of world modeling, and I hope we can, hear also some background secrets here on what we can do with world modeling. Yeah, so please welcome Gianluca. Thanks.
Thanks, Adam, and yeah, thanks for having me. I'm gonna try to be as loud as I can. If you can't hear me at the back, wave. I'll try to. You can't hear me? No? Okay. I'll be louder. Okay, today I'm here to talk about generative modeling, of course, but more in general about embodied AI and autonomous driving. I always like to start with this picture when I think about embodied AI and
Working.
all right, great. And so what's embodied AI is like an agent or an intelligence that can be out in the world. And when I think about the world, I think about this picture. This is an actual intersection in central London. And yes, a car can drive there. And so, yeah, when I think about autonomous driving, I really think about this is an embodied AI problem. We need to figure out how to take intelligence, put it in a robot that it will interact with the world and in a safe way. So that's just an example of what it means to do that. This is some actual footage of Wave car driving in London during traffic, and there are roadworks going on, cyclists coming, and we need to merge into the traffic. So I think this is just one example of the complexity of the real world embodiment for AI. And what I'd like to show today is a little bit of a high-level introduction to how Wave is approaching this problem. I think historically, the AV industry approached the problem of solving self-driving through this AV 1.0 approach, which has very clear separation between a perception stack, a planning stack. Each of these stacks are full of components. Each component is highly engineered, sometimes rule-based. At Wave in 2017, we decided to change that. And we decided that probably this embodied AI is an end-to-end problem. What that means is it's just one stack. It's an end-to-end network that can learn to go from images straight to actions. And why did we think that that's the way to go? So I think the promises of end-to-end driving are very, very appealing to solve this problem. When we think about being just computationally homogeneous, this network can be highly portable. It's just a neural network. In order to use it, you just have to be able to do a forward pass on some hardware. It's agnostic to vehicles and sensors. None of these stacks are highly engineered around a particular sensor type. They're just images and videos going into a network and actions coming out from the other end. It allows a little bit to be more agile when it's time to develop these networks because it's just one network or let's say a few modules. And what we believe is this will have and has today superior performance than just human coding. With human coding, I mean writing rules on how to approach all these edge cases and so on. And again, just think about the video I just showed you. How would you hand code the rules to solve that situation? And so it becomes increasingly complex to get into detail, and we think end-to-end driving is the way to go. So here again, some more examples of what do we think is like starting to see that, it generalizes to long tail scenarios, like a car backing for several yards, and we're just understanding that this car is not coming towards us, and we're just able to follow and keep driving while this car finds a parking spot in busy London. We go around it, and yeah, we just keep going. And another great example of why end-to-end driving is very powerful is it generalizes to different vehicles. So some time ago, we managed to prove that we could train just one network to drive different vehicles. And these different vehicles are passenger car and a small delivery van. And what you can see in the video on the right are actually the van driving behind the car. And it's the same network driving both models, executing correctly actions and driving around London. And it's just one network. It's been trained on data collected from both vehicles, and it can generalize from one platform to the other. And this is very important because if you want to embody autonomy, you can just take it, there is a new vehicle, you just put the network in, and it drives. Very like humans, right? If you change your car, you can still drive. If you jump on a van, you can drive. So yeah, that was like a brief introduction of what Wave is, how we're approaching this problem. And today I want to dive a little bit deeper into some research areas that we're focusing on that we think are important to develop embodied AI for autonomous driving. So, but first, let's start with like some open research challenges. Right? For autonomous driving, explainability will be important. Right? We will ultimately have to prove or convince people that the decisions that we're making are sensible. And so what's one big challenge is like to open that black box that is a large neural network and make it like more explainable, interpretable. Another thing is, how does this scale to very long memory? When you think about scaling an end-to-end network, and you want to have reasoning over, I don't know, the last 30 minutes of what you observed, this is very hard to scale to that kind of memory. So how do you add that kind of reasoning and prediction into the network? How do you even change the rules of how you drive without retraining the network from scratch? And you can think about rules of the road changing. And what do? You just go and retrain your whole network, you recollect your data. You can't really do that. So how do you extend that intelligence to be reprogrammable? And of course, end-to-end requires a lot of data, and it's very expensive to get edge cases. And these are just some examples of things you might encounter out there, like novel combinations, like a reflective surface and a large truck or a zebra in the middle of the road. Or again, this is just a fun video of, I think, a bachelor party in London, but people sometimes get creative and decide to dress as traffic cones. And so we think that the solution is to use generative text and video models to supercharge AV 2.0. And this will allow us to solve a lot of our data problems, add reasoning into the models, and as well as explainability. So today I want to touch on three main points. One is like, what happens when language meets driving? What happens when you have access to a generative world model? And I would also like to talk about like neural replay. So let's start with language meets driving. So what does it mean when language meets driving? It's just when a language model that can take sensory inputs from a robot, in this case, a car, and you can interact with text, can really help in terms of like explainability, the intelligence that is in that AI, and also like boost trust and safety. So for this reason, like around a year ago, well, we launched Lingo 1. Lingo 1 is a grounded video VQA model, which took video snippets, and then you could converse with this agent. This was fully offline, so you could just upload a video footage of driving. And what Lingo could do is, for example, do some commentary. Here, there is some footage of driving, and there's Lingo commenting on what's going on. And it's clearly like able to explain the reasoning behind why a driver would be doing certain things. At the same time, we went with a full VQA demo where if you just converse with Lingo about a driving scene, maybe here you can't read, but it's too small, but we're asking, you know, if you see any cyclists or what do you see around you? And it's pointing out at the delivery van on the left, et cetera, et cetera. And also last year, this was extended to full referential segmentation where Lingo could point at things in the image so here we're saying what you're paying attention to. And what Lingo can do is saying, I'm focusing on the drivable area, which is the part A, to ensure that we stay within the lane. And I'm also monitoring the traffic, et cetera, et cetera. So Lingo now can point at things. And so this is the level of intelligence that you would expect someone that is driving your car to have. And, you know, we were very pleased to have it. And so what we did next is we fully grounded vision, language, and action models into a single model. And that's what we launched recently. It's called Lingo 2. This is like fully grounded. It's a video, text, and action model, which means that this model can drive and explain its own action while driving. And so this is just, I'm going to show like a little bit of this video. It's a very long video of actual footage of Lingo 2 driving in London and explaining its own actions. And you know, if you read, you can see that it's paying attention to the right things. It's able to explain what it's doing and why it is doing it. Yeah, here, like, you know, we're just turning to follow why we're turning because we want to follow the route. And I mean, here there's not a lot more happening, but I can probably skip ahead and see what we got to. Right, so here it says I'm accelerating, changing lanes, and so on and so forth. So I think we believe this is like the first language model that's actually driving a car in a real embodiment. Other things that we could do with Lingo is we can even prompt the model to have certain behaviors. This is the footage I'm about to show you is all from our closed loop simulator. We actually didn't do this in the real world, but basically is the same scenario, which is we start behind a bus, a stopped bus. And in one case, we can ask Lingo, we want you to stop behind that bus. And what we can see is that Lingo can respect our prompt and actually safely stop behind that bus and leaving space for the bus to merge. In the other case, we're more aggressive and we just say, please overtake that bus. And we can see that from the start, the policy has much higher speed and it just overtakes that bus. And this is all done, same policy, just different conditioning through text. So what's next? What's next is we believe that multimodal training will be very important because just look at the image on the left. Yes, you can learn something about it. You can learn that maybe you have to be stopped. There's a zebra crossing. There are pedestrians there. When you read the text on the right, that text might be worth 1,000 videos because that text explains you how to behave in this kind of scenarios. So what we believe is that merging like video and language training into a single model will really boost the kind of intelligence that we can put in our vehicles. Up next, generative world modeling. This is a project I'm very close to, and I'll try to be unbiased, but I really like it. So I always start with this case. If you just look at the image on the top, it's just a static frame. You don't really know what's going on. As soon as you watch the video, you understand that there is a car that is to our left that is stopped, and you're just following the white car in front of us. So what does this tell us is, in order to drive well, you need to be able to predict the future and be able to like reason about the possibilities. Until you saw that video, you didn't know if that car was stopped or not, but somehow you knew that those are the possibilities. It could be stopped, it could not be stopped, not much more, right? And what we noticed is that since 2022, maybe the end of 2022, there's been like a huge increase in publications in the space of world modeling, specifically for like autonomous driving. And yeah, I just like to point out that we've been thinking about world modeling for a very long time, where I think the first work where we demonstrated the use of world models in a real robot dated back at 2018, where on our old vehicle, a small Twizy, we managed to train a policy fully in imagination to drive that small Twizy down a country road in Cambridge. And from there, we went through like Fiery, which was a paper we published in 2021. It's a world model that can predict the location of all the other vehicles in bird's eye view. In end of 2022, we published a paper called Mile, where it's the first time that we merged world modeling with a driving policy on a larger scale. And in 2023, like a year ago at VPR, we unveiled Gaia, which is the most ambitious world modeling project so far that we've done at Wave. And this is an autoregressive transformer model that can generate and learn from videos. It can be prompted with text. We can control the ego agent behavior with actions. So here are just some examples of what we saw after we trained Gaia. Is like we started to see this kind of emergent behaviors where Gaia could understand that starting from the same point, there are multiple plausible things that you can do. So here in this case, like you're at roundabout, you can go straight, you can go right, and Gaia can just imagine both. Other things that we saw, the interactions with other agents can be different. And this is similar to the case that I showed before. One, it's real world, this is fully generated. So Gaia understands that there is a car is sticking out from a side road. That car could just decide to back or just merge, and both options are valid, and Gaia knows about it. Then what we try to do next is like even simulate some edge cases. So what we did here is, because we can force the ego agent behavior, we forced our car to go in the opposite lane. And what Gaia imagines is that the oncoming traffic would react to this to try to avoid the collision. That's plausible. That's what I would expect the other car to do. And none of this is scripted. It's just fully generated, and Gaia understands all these concepts. Other things we could do with Gaia, control the generation and generate samples under different weather conditions or time of the day. All this done by prompting with text. And we can do snow in London, which is not that common, or all of these things. And ultimately, what really impressed us is like we could generate minute-long videos of plausible driving. This is at 2x speed, and this is fully unprompted. We just asked Gaia draw us a sample, and we kept going for like minutes and minutes of generation. And yeah, it keeps going. Everything is plausible, and there is always something interesting happening. So we were very happy with it. And yeah, last but not least, we can condition with language, we can condition with action. When you start combining these, you start to get close to a place where you can control what you generate quite well. Like, for example, you would just say, you want to accelerate and steer a little bit to the right, and there's a bus 15 meters in front of you. And when you do that, you generate a scenario where you overtake a bus. One thing we haven't shown in the Gaia 1 launch, but it's something that we've been working on more recently, is also like controlling other dynamic agents. Because the same way we control our behavior, we want to control other agents' behavior. And so here are like just some quick examples of what we can do with it, which is we can just place agents in different parts of the image, and everything else around them is generated accordingly. What we can also do with this, and that's the top right corner, is that we can actually take a real image and we can decide to paint agents in it. And this is the example. Like there, we would like to have a vehicle in there, and that's the result. There is a car added to the scene. Everything else is the same. The car is there now. And how does that look when you extend these to like videos and multiple cameras? And it looks like this. So what you're seeing here is everything that is starting in that scene. It's from a real video. And all the agents, pedestrians, cars that you can see, been fully injected by Gaia. They weren't there, and now they are. And we were really impressed to see that even extending this to like the multi-camera setting, if you look at that black sedan, it's correctly placed in the world, in the 3 cameras, and none of this has been, there are no inductive biases, not 3D inductive biases, it's just fully learned from video. So what can we do with this now? And we use this in conjunction to Lingo 2 to basically prove that Lingo 2 can reason about the correct things. So what you can see on the top is like some original scenario that we collected driving in London. And that's the explanation that Lingo 2 will give and the action that Lingo 2 would like to have, right? So in top case, like says, we're just increasing the speed to match the speed limit. Road is clear ahead of us. What we do is then we inject the car in front. And now Lingo wants to slow down and says, I'm slowing down to match the lead vehicle speed. So this is allowing us to do this counterfactual reasoning where we convince ourselves that this policy, like the Lingo model, can correctly drive and also reason about it. Similar example there. In one case, we say we're stopping because there is a red light ahead. As soon as we put a car in front, the red light is still there, but of course now we're stopping because actually here it says we're stopping because there is stationary traffic in front of us. Last but not least, again, we can go even more towards like generating safety critical scenarios. Here are just a couple of examples where we set up the scenario where we are overtaking some large vehicle, like in one case it's a bus, in the other is a van, and there is a jaywalker on the street. This is fully generated by Gaia. So what are the opportunities ahead? Is like, again, Gaia is very intelligent. It understands a lot of things about the world, how it works, and integrating this with our on-road driving is really important. We're going to think about further scaling up, going to multi-view generation. I mean, I've shown some sneak peeks of some of our 3-camera generation, but we want to extend that, go multi-sensor, and use this learn simulator for training and evaluation of our driving models. So trying to wrap this up, but basically that's what we believe is like if we just collect data in the real world, that's how we're going to scale at collecting edge cases, right? We're going to become rarer and rarer and rarer. And what we think is to really supercharge these, we can use generative AI and something that is neural rendering. So together, when we merge generative AI with neural rendering, we can really boost the number of edge cases that can go into our training set. So let me briefly touch on neural replay and novel view synthesis. Because yeah, I'm really glad to huge congratulations to the team that unveiled yesterday the new model. It's called Prism 1. And this is like a new model that we use a wave to do scene reconstruction for dynamic scenes. And these are just some examples of dynamic scenes reconstructed from our London data. And we similarly reconstruct scenes in the Silicon Valley, all from the same model. And what we can do with this new, we can start doing, for example, novel view synthesis. And here are just some example of a reconstructed scene where we can freeze the position of the camera and we can let time roll forward and backward. Here's another example where instead we freeze time. Well, you see in all videos, sometimes we're freezing time, sometimes we're freezing the position and letting the other one roll. But that's just to demonstrate like how good novel view synthesis can be once we have these scenes. And show you some more examples. And all of these models are just learned from cameras only. Like just use camera images, like surrounding cameras. And you can notice like in this example, like we freeze the position, but time is rolling and the traffic light is changing color. And similarly here, if you pay attention to the blue car, you can see the wipers are still going. So it's like the attention to detail is really important here, and we're mind blown by these results. And here are some more examples where we can even predict, like we can even fit in the scene some of geometry and motion prediction. So yeah, just to wrap up, together with Prism One, Wave also launched Wave Scenes 101. This is a public available data set, and this is a public available data set that we came up with when we were developing this model. The reason why we did that is because we couldn't find a public available data set that would really fit our needs. And what this data set is special because we think it's the first data set that has a full evaluation camera, and the camera rig is positioned in a way that the two side cameras contain all the information that you need to reconstruct the middle camera. So that camera can be used as a test set for your novel view synthesis. So we decided to release this data set. It's 101 driving scenarios from the UK and the US. The link is there, or just go on the Wave website. You'll find the link. If you're interested in like neural reconstruction, please play with this data set and let us know what you think. So finally, unlocking embodied AI at scale. So here we touched on a lot of things, right? What happens when language meets driving? What happens when you learn models of the world by predicting the future? What happens when you use neural reconstruction? So what's next? It's like we believe that all these things can come together into a single large foundation model. And what that means is we can train this model on diverse data sets that have access to diverse sensory inputs that solve diverse downstream tasks. And even in diverse embodiments, cannot just be limited to driving vehicles, and just pre-train this large foundation model. And that's what we really believe will unlock the full potential of AV 2.0 once all these things come together. And I think a way we're like kind of leading the revolution of embodied AI for autonomous driving with like language, word model, neural replay, really supercharging AV 2.0. And foundation models, again, they will unlock the full potential of it. So stay tuned. And just to finish my talk on time, a Wave, we're hiring. There's a link for some open roles. If you're interested in like having a conversation, please come meet the team. We have a booth at the expo that is starting tomorrow. So come say hi. I'll be there. A lot of the Wave team is here this week. So come find us, have a chat with us. And we're always glad to talk. Thank you very much.
Fantastic talk. We have we have reserved 10 minutes for questions, plenty of time. Let me start maybe with one. So how fine-grained do you think could you make this control also in terms of generating edge cases like, upside down cars or cars opening doors or kids running in Superman costumes across the street? Is this something that you will get easily to, or?
Yeah, I think, easily is maybe a strong word, but I think, again, when you start combining the power of language and supervised video modeling, I think all these edge cases become less edge casey, right? Because what you can do is, at the moment, we can place a car here and there. But once you merge this for driving, you can ask for this car is upside down. And when you train this foundation model, or like when you start combining all these tasks and you train them like an internet scale, we've seen plenty of demonstrations of this kind of next level generalization and compositionality of concepts just coming out of nowhere. And so, I'm not going to say it's easy, but we do believe that's exactly the way to go.
So scale will actually
allow scale and multimodal training. Because I think once you combine the video training and text training, should be a lot easier for these models to generalize to this new concept and these edge cases.
Okay, thanks. More questions?
Thank you, great talk. You presented that in your models, we use, click like encoders and other vision language models, right? So there has been a lot of work which shows that click like models and then diffusion models and then auto-regressive VLMs, they don't really have a very good spatial understanding of things, right? They don't really understand spatial relationships and treat things as bag of words. So especially in a real world application where these things will have real adverse effects, do you think these models in their current form are suited to be used in applications that
yeah, thank you. That's a great question. I don't know if online they can hear us. I'm just going to try to summarize. But yeah, we've been discussing about like the use of clip models and the fact that they've been shown to just basically learn a bag of objects and whether these are appropriate for like real world embodiments. And yeah, I would say short answer, yeah, it's no. And let me try to quickly go back. In fact, maybe it's just a small detail, but yeah, we use clip in Lingo 1, and this model was fully offline. So that was just grounded video question answering model, and that worked very well. But once we move to like Lingo 2, you can see that it's kind of disappearing, and the Lingo 2 is the model we actually embodied. So yeah, I think you're right. We've seen that other pre-trained models that we pre-train are a little bit better at this, and so that's what we decided to embody. Thanks for the question.
There are some conditions and we need to meet out that in some kind of generation. I'm interested to know if there anything you have done for evaluating those conditions.
So this is some slide. This is some very early work that we've been doing. And so what we've done is we use Gaia to add agents into real driving scene, and then in open loop, test that Lingo can appropriately change its own action and also explain why it is doing that. So at the moment, this has been like a very, I would say, manual process, right? Because it's not trivial to define, given this modification that I've done, what is that I'm expecting? Yeah, I think you're right. And so yeah, we started from here, and you know we're scaling this and figuring out. But for now, it's like we're just really happy to see that a model can reason like this and understanding. You know, I was stopping for a red light, and now I'm stopping for traffic ahead of me, which really gives us that conviction that these models are paying attention to the right things.
Mistakes that the
Oh yeah, I mean, yeah, I can share some funny stories about Gaia generation. So usually, like, the issue is around hallucination, and I mean that's expected. I think everyone that is working in generative models knows. And so once you start, if you like, fully like if you try to do unconditional generation, this hallucination is a superpower of Gaia, and it's what's allowing you to generate 2 minutes long videos, because it's hallucinating things that don't exist, but they're all plausible and they do make sense. Once you start tying this with some other high-level controls, like you're forcing the car to turn right, as soon as you turn, you don't know what's there. And so if you're forcing a very specific path, Gaia could actually generate something on that path that makes the car collide with what's generated. And so if you just go from the validation perspective, like that's a little bit tricky. And that's why we're kind of thinking that generative models are superpower, but we're also coupling them with neural reconstruction to basically get the best of both worlds, I'd say.
Can you still use it as a landing model? For example, if you ask it what's the largest city in the UK, and also what happens if you say like drive to the wall? Are there any guardrails?
No, yeah, you can actually do that. Actually, we could do that even with Lingo 1, even before. I think last year at ICCV we had at our booth we had a demo. Everyone could just come and talk to Lingo about the driving scene, and that's actually what most of the people tried to do. It was just talk to Lingo about something else. And yeah, it still maintained quite a lot of that information. Not perfectly, but yeah, in most of cases we could see that Lingo could answer like random trivia questions that people would ask and ignore the image input because it wasn't relevant answering any of these questions. And often was also pretty honest about not knowing information. But yeah, that was pretty interesting because it's something we kind of discovered by allowing other people to play with Lingo, because we didn't really think about that much. But it seems, yeah, people come and poke into Lingo once you give them access to it.
So the second part, I think, was also about the guardrails. How would you actually integrate guardrails into the system? Like, you know, telling it to drive now into the storefront here to the left. I mean, I guess it should not do.
Right. So the guardrails are kind of emerging properties of the data you train on, because it's just implausible, right? You've never seen, when we train Lingo model to drive, you've never seen that action. So why would you choose it? So the guardrails are kind of implicit, but at the same time, again, one of the things I've mentioned in the opportunities ahead of Lingo is this multimodal training, right? So this is where guardrails will live in the text. And you can explain a lot of things, maybe saying, you know, it's customary to leave a couple of meters from the pedestrians that are crossing the road because that is nice to do, don't get too close. And then, you know, you can change that. You can say, maybe now it's better to have 3 meters. And actually, that's something we started thinking about because in the United Kingdom, they changed some of the highway code like a few years ago, where they decided that now you have to leave more space when you overtake cyclists. And that's when we actually started thinking about all of this, because we're like, okay, how do we do that? Because we have data collected where we don't do that. And now we have to change this behavior. And so if you explain and you do this multimodal training, that's probably the way where you're going to be able to explain all these things to the model.
Okay.
How does the multimodal training handle situations where, like, there might be two sort of harmful options, but one of them is worse than the other? Like, is there some kind of metric for scoring that?
No, I think metrics for scoring that there isn't. And I think it's also dangerous to try to come up with one, because chances that you just get it wrong are huge. But we believe that, you know, multimodal large-scale training is going to build the foundations of the intelligence. And then you can always fine-tune your driving model on some very small, highly curated data. It's very similar to like how humans learn to drive, right? You don't need too many hours of driving before you learn how to drive, and they can be highly curated by a driving instructor. But that works only once you build on top of with human intelligence, you can learn to drive in 10, 20 hours. And that's the same, like multimodal training and foundation models are going to build a foundation that allow us to safely train on highly curated data.
Okay, with this, we unfortunately need to stop.
But yeah, if you want to chat more, you'll find me at the booth tomorrow. And yeah, I'll be around all week. Thank you very much.
Thank you, Gianluca. Fantastic.
Very compressed. If you do the in-painting,
Yeah.
like you do it like on image level, and do you have any other control to in-paint?
Okay, so with this, we come to our second speaker. It's my great pleasure to introduce Siyu Tan, assistant professor at ETH Zurich, very well known for her work on digital humans. Super curious to hear her opinion on this topic. I think a little bit more on the explicit inductive side on generative modeling. So we are going to see like back to back, really, from the different spectrum of generative modeling. So really curious to hear what you're going to say.
Thank you very much for the introduction. Can you hear me well? People in the back? Yeah, okay, good. So yeah, so we work a lot with generative models, and today for this talk, I will talk about generative models for human motion estimation. So very specific topic. Yeah. Does it work? Yeah, okay. So yeah, people are talking about the age of autonomy, right? So people are building like, for example, autonomous driving cars, autonomous robots, and also embodied devices. And I think these are all very exciting opportunities. And so in order to let autonomous agent or intelligent agent to interact with humans and work together with humans, they should see and understand the 3D world around them as well as the humans, right? Human motion, human pose, human intention, and also like to predict future motion. So I think that's really important. So motivated by this, it doesn't work again. Okay, motivated by this, in my group, we have been working on 3D human pose, motion modeling. And today I want to talk about 4 work. And the first one is, so our very first work on human motion estimation from monocular videos. And the key idea there is actually a learn motion prior. And the second and the third ones are on the egocentric human motion estimation. And here, actually, we leverage the generative models, diffusion models, to help us to model the uncertainty and also to model the human-scene interaction. And the last one is the latest one, which will be presented in 2 days. So it's our very recent work on human motion estimation from monocular videos. Again, it's we leverage actually diffusion models for this task. Okay, and all this work are actually led by one PhD student, Si Zhang. Yeah, so I will start with a human motion capture, a bit of motivation. So, I mean, for people here, probably you know, like the best human motion you can get is probably using motion capture system, right? Where you put markers on body, on face, on hand, and you have lots of mocap system, and then you can really obtain or reconstruct a nice natural human motion. For example, this is an AMAS data set. And to me, these motions are quite natural, and these are actually reconstructed from mocap system. However, what we want to do, right? If we want intelligent systems or agents to interact with humans, we cannot just capture human motion from mocap system, right? We want to capture human motion just from a monocular camera. And here is a monocular RGBD camera. And this prox, I think, was one of the first works which can reconstruct human pose and motion from monocular RGBD camera that consider also 3D environment, right? To reconstruct the human environment interaction from this monocular camera. But you can see the motion quality really drops, right? Like the motion is very jittery, and also like it's not natural. And our question by then is, how can we reconstruct natural and smooth human motion in 3D scenes with a monocular camera? And our key insight by then is to learn motion prior from high-quality mocap data. For example, AMAS data has hours and hours high-quality motion data. And our first work was very actually simple and intuitive. So I'm going to just explain a little bit in details. So when we try to reconstruct human motion, right, a 3D human body, like a 4D human body, right, over time, the first question is what kind of representation we want to use? How do we represent 3D body over time, right? And by then we use actually marker-based representation. So basically we predefine a set of markers on body. And how to represent human motion? We first compute the velocity of a marker in the nearby frame, right? For example, this marker on the foot. And then we compute this velocity for all the markers on human body. And then we compute this velocity for all the nearby frames, and we get an image, right? So now we can represent human motion, 3D human body over time with an image. And with this image, you can see this dimension is the velocity of certain marker, and this dimension is the velocity of all the markers at a time step. And the next thing what we did is very simple. So given these images, we actually get this training data, these images from AMA's data set, which contains hours and hours motions, natural human motion, which means we have lots of such training images. And what we did is basically we train an autoencoder, right? So the first thing is there's a reconstruction loss to reconstruct the input. And the second thing is we want to learn a high-dimensional latent space where the human motion is smooth, right? So we add a simple like loss term to penalize the first order, right? And this actually gives us a very smooth latent space of human motion. And next, I will show you how did we use this very simple autoencoder to reconstruct natural human motion. Okay, so now this is a test sequence, right? We never seen that during the training. And now we basically run this, give this test sequence to our autoencoder. And you can see the motion is smooth. The representation is quite smooth as we expect. And now, if we give this autoencoder, the encoder part, the previous state-of-art result, like this monocular RGBD reconstruction, and you can see the latent space is quite jitter, right? So this is basically because our autoencoder is really trained with high-quality smooth human motion. And what we did next is basically to penalize again the first order difference in the latent space. And instead of update the model, right here, what we did is basically to update the or to optimize the result such that latent space becomes smooth again. And you can see when we backpropagate this gradient to our input, and the human motion becomes much more smoother and natural, right? So this is a key idea of this work, and this is the motion prior we were talking about. And here I want to show you some more results. And here is the input, again, monocular RGBD sequence. And this was a previous state of art. And then this was our result. The motion becomes much smoother and also natural. And the whole algorithm is actually a big objective. We have an optimization algorithm for this. So what I explained is basically the motion prior, the key component of that optimization problem. Okay, so that's the first thing we did. And the next thing we try to do in my group is we try to reconstruct human motion from embodied camera. So I'm very interested in egocentric perception. And for egocentric perception, back then, actually, there was no really big data set where you have the 3D human ground truth for interacting people from the egocentric view. So that's what we did. We collaborate with Microsoft and we capture this ego body data set. So basically, we have one person, two people in the environment, like a social interacting with each other. We have one person wear a HoloLens. And we also have a few Kinect camera, and then basically we can reconstruct the 3D human motion from the few Kinect, 3 to 4 or 5 Kinect cameras, and we synchronize these Kinect cameras with a HoloLens camera, and now we have a 3D ground truth from this egocentric point of view. Right. So we captured I think more than 10 in more than 10 office many data. And in the end, you can see this is the data we have. So we have 125 sequence and 15 indoor things. And for all this data, we have the human motion ground truth as well as the egocentric view and gaze direction, hand and head tracking, as well as 3D scan of the environment. Okay, so now with this data set, the next thing we want to do is to reconstruct human body, not motion yet, but first the human body from this egocentric point of view. And this is actually a very, very challenging task. So for example, these are two people interacting with each other, right? And our goal is really to reconstruct this human body from this egocentric view. And then the problem is for this egocentric view, especially when people interacting with each other, there are always truncations, right? Or human see interaction, we don't really see the full human body. So it's a highly ambiguous task. And one idea we had at that time is because like we are talking about embodied devices, right? And lots of them come with like a rough understanding of the 3D environment. And the assumption we made at that time is basically, let's assume we have a rough understanding, rough point cloud of a 3D environment. And given this point cloud, now let's develop a model that can really reconstruct the human body that have a natural human-scene interaction. For example, when we consider this 3D scene, rough understanding of the 3D environment, and then we know like this is a right estimation and this is a wrong estimation. Okay. So that's the key idea. So the key idea is given the monocular RGB image and give a rough 3D point cloud, let's reconstruct human body. And then how do we do that? So this is a highly ambiguous problem, right? So we don't really see like the full body. We often just see the upper body, and we need a probabilistic modeling. And on the other hand, right, on one hand, we need a probabilistic modeling. And on the other hand, what we need is to really make the model condition on the environment. So then what we were thinking is basically now given these two requirements, let's design a diffusion model. Right, diffusion model, we can basically consider the environment, 3D environment, as well as the input, like a monocular RGB image, as well as the body detections. We can use this as a diffusion conditions to train our diffusion model, right? So a bit of detail. So our diffusion, like a denoiser, is actually a graph convolutional neural network. The reason we are using that because we are interested in human body, and we want each body part to be conditioned on the environment and to conditioned on the image observation. And by leveraging this graph convolutional neural network as a diffusion denoiser, we were able to condition this prediction, right? This denoising process on the images and on the 3D environment. And another thing we did here by leveraging diffusion model is to basically design a collation score guided a classifier, in the sense like when we do the denoising process, we can further like refine our output based on the human-scene interaction collation, right? So that's another thing we did in this work. Yeah, here it is. So as I mentioned, so we have the denoiser, right? And for this denoising process, we can define a collation score guided sampling, which basically computes the gradient with respect to the pose parameters and kind of guides the pose parameters in the way that there are less human-scene interaction. And you can see with this collation score guided sampling, we can basically have a better human-scene interaction here. Okay, and what in the end this Ego HMR achieve is, first, it achieves like a relatively accurate body estimation for the visible body part, and plausible human-scene interaction for the invisible body part, right? So here you don't really see, but actually these poses are plausible if you consider the environment, and as well as diverse sampling observed body part. So here we only observe the upper body and also the environment. And for the lower body, you can see we have a diverse sampling. And also here, there are more results. So this on this side, here is my mouse. Yes, on this side is the input, and this is a 3D environment and egocentric view. And here are the results. And these are the different sampled like plausible body pose. And here you can see it's generate sitting pose, but with different like poses. Okay, so that's about egocentric pose estimation. And the last one, the work I want to discuss today is ROM, robust human motion reconstruction via diffusion. So again, it's a diffusion model, and this will be an oral talk on Thursday, and the poster session is also on Thursday. Yeah. So the first thing is, let's think again about this monocular human motion reconstruction. So what are the key challenges here? So if you look at here, actually, one key challenge is really noisy detections. So here we see really like very noisy 2D detections. And the second challenge is occlusions. So this is the state-of-art motion reconstruction from this monocular RGBD camera. And you can see when there is occlusions, we don't really recover the human dynamics here, right? And for ROM, so in order to basically solve these tasks, we developed ROM. It has a few key advantages. So the first one is this motion recovery is in the global space. So we really get the global 3D human motion. The second is it's robust to noisy and occluded inputs. So you can see these detections are actually occluded, but we can still get the human dynamics, the motion out of this like highly occluded test cases. And also it's much more efficient than optimization-based approach. For example, compared to humor, it is 30 times faster compared to that. Okay, so what's the model? So I will try to explain to you. It's a little bit complicated, but I hope you can get the idea. So the input is again a molecular RGBD video, right? And we first have an initialization. So this initialization can be flexible. It could be some human mesh regressor or some optimization-based approach. And given this initialization, normally what you get are noisy and incomplete pose and route trajectories. So you get something, but it's noisy, it's incomplete, and also you also like this route trajectory is quite like a jitter, right? So given this noisy and incomplete pose and route trajectories, the task now is how do we really reconstruct smooth and natural human motion? So the first key idea is let's try to model the route trajectory and the local pose separately. So based on our experiment, this is actually a quite good choice. So we design like a diffusion model just for the route trajectories and diffusion model just for the local poses. And it actually makes the learning much easier. So this trajectory nets and pose nets were able to produce something quite reasonable, right? So a little bit in detail, so this trajectory net is a U-net architecture, and given the noisy and incomplete route trajectories, it can estimate like a smooth route trajectory. And for the pose net, so basically the goal of the pose net is to estimate the body pose. And then the input to this pose net are the incomplete local poses as well as the estimated global trajectory, right? So this pose net actually take the output of trajectory net into account. And this already actually gave us some reasonable result, right? If you combine this route trajectory and the pose estimation, it can give you some global 3D motion, but there is a problem for that. So when we really estimate the route trajectory, we only take the implicit and noisy trajectory into account, but actually the local pose, how body moves, also give us lots of information about the global translation rotation of the body. Right. So what we did here is basically, let's try to design another component, which when we try to estimate the trajectory nets, let it also take into take the pose net, like the local poses into account. And how we did that, we basically designed this trajectory control like a model. So just a little bit of in details, as I mentioned, right, this trajectory nets is a U-net architecture. And in order to really take to fine tune or to refine the trajectory based on the local poses, we designed this trajectory control component inspired by control net. So this takes the local poses into account, and then this basically gave us a better or new global trajectory. So again, the whole picture, right? So we given this incomplete global motion, like a global trajectory and poses, we have the trajectory net and pose net to produce the global trajectory as well as the local pose. And then the next thing is we basically have this trajectory control, which takes the local pose into account to refine the trajectory, the global trajectory. And then what we can do next is actually to run this in an iterative fashion. And in our experiment, we basically ran twice this iterative inference, and we can basically get a quite nice, like a global human motion. And I want to show you some results. So you can see here is the input. And this is actually the ground truth. So this is like a jittered human motion, right? And this is a result from humor. I mean, you observe it lose like this dynamics on the lower body part, right? And with our model, you can see it actually can very nicely reconstruct like this motion, for example, walking motion, right? Without really lots of artifacts like foot skating. We don't really see lots of foot skating here. And we also ran this on real world data, of course. So this is the input again, and this was a state-of-art result humor. I'm not sure whether you can see it clearly from the screen. So when there's like a occlusion, it loses the dynamic, loses like a human movements, this type of things. And then with a diffusion-based this ROM model, you can see the human motion can be reconstructed quite nicely, I would say, even when there is really like a high occlusion case, when human body is really occluded by furnitures or by other things. And there's more results. So yeah, so this is another baseline called FaceMP. And it has some like a jittering problem, not jittering, but kind of flickering problem. And we also, okay, that's all the video I have. So just a summary, with ROM, what we can do, what is basically we propose this model, we model human motion with diffusion model. And this, what we found is this is very effective for incomplete observations, right? Noisy and incomplete detections. Body part detections. And we propose this control, like trajectory control, to capture the trajectory pose interdependencies to produce like a kind of a coherent 3D human motion. And it's compared to the optimization-based approach, for example, humor, it provides us like much faster inference time. Of course, there are also limitations. So the first one is actually the generalization to out of distribution body shapes is very limited at the moment. And also we haven't really considered the scene constraint in our model. And we don't really, I mean, we lack of data for such of, to really model human scene interaction in this model. Yeah. So again, like I present these 4 works. You can find the code, data, and model on our website. So this work has been done by these wonderful collaborators, and especially Siwei. She has been leading all these 4 projects. And just if you are looking for someone working on human pose estimation, you should consider reaching out to her. She's wonderful. Thank you very much.
Okay, thank you for this fantastic talk. We have plenty of time for questions, and let me start maybe with one.
Yeah.
I mean, so there's so much data on these, like it's such a big field, you know, digital humans. Do you see like a way towards like a foundation model for humans, and how would this look like? I mean, also in the context of, you know, what we've heard earlier, I think like, you know, do you see something like this coming?
So I think, I think depends on what do we mean by foundation models here? So I was attending the talk yesterday by Michael Black, and he was arguing like simple is already like a kind of a foundation model, right? In some sense. So I think really depends on the foundation models. So if we are talking about like a human movement and text semantic, and now we have like AMAS data, and also people label a lot of like a human movement. So I think we have data that can kind of enough for us to start to do something. Yeah. But I think ultimately we really need to leverage the internet scale data, right? For YouTube, we have so many human like centric data, right? There are so many data about our daily activities, and sometimes there are also texts, right, with that. And also if you think about movie data and how to leverage those data, I think that's a really challenging question, and the key question to really build kind of a multimodality generalizable foundation models.
You have an idea how to do this?
No,
Okay.
no, I have some guess.
Yeah.
So one thing is we can talk this for very long because I've been thinking about it. Yes. So I think one thing is how to say that. So so people always think like, right, if you want to, we always, so people say like, let's try to reconstruct human motion from YouTube video, because YouTube video, they have so many different human movements, right? And then maybe we can train a motion model, we can train a human behavior model based on our reconstructions, right? But that is really based on assumption you can reconstruct human motion from those crazy videos.
Yeah.
But now I have a question. Do we really need to do that? It sounds like a chicken egg problem, right? But if you think about, maybe we can kind of not really, we might not need to really go into the explicit 3D representation in the sense like explicit 3D body reconstruction from this crazy in the wild videos, right? Maybe some text input is already good enough text annotations, and maybe some foundational 2D video models, right? I think how to really kind of distill this 3D knowledge, body movement, body behavior knowledge from the foundational models, right? From 2D foundational models, I think there is a kind of opportunity there. Yeah. I don't know, but that's my guess.
I think that's also like an idea actually that, you know, like other video world model, you know, ideas that we've heard already,
Yeah.
like in a sense, you don't have like direct access to the 3D from
Yeah.
those, right?
Yeah.
How to distill this is
Yeah.
maybe something interesting.
Yeah, I think, yes.
Yeah, no, like,
Yeah, I agree. I think maybe we don't really need to go through the explicit 3D reconstruction, although the whole work is the whole talk about 3D reconstruction, but maybe now it's time to think about not explicitly reconstruct those things.
interesting. More questions? Anyone? Well, I can continue. So maybe like one from the thing that I'm thinking about when you talk about, you were talking about occlusions a lot, right?
Yeah.
So, I mean, that's interesting. It's challenging. Everyone knows, but how to evaluate, you know, whatever happens behind the occluder, you know, how can we actually benchmark this, since there is like, there is no ground truth in some sense, right? We can eyeball it and say plausible, but there are so many solutions. So is there like a way of quantifying the performance behind the occluder?
Yeah, so that like so there are some data, but very limited data, right? For example, this ego body data set, from egocentric view, you're occluded, right?
Yeah.
Like the legs, but actually we have Kinect.
Yeah.
3, 4, 5 Kinect. If the Kinect CEO, we probably have a pseudo ground truth, right, to estimate that. So there are data to do some evaluation, but I think it's very limited. The amount of data is very, very small. And maybe, I mean, I haven't checked the latest work, but maybe some on-body device, right? IMUs or other sensors, on-body sensors, not really rely on explicit or external vision sensors.
Yeah.
Maybe those are the ways to go. So to capture large scale data. Yeah.
Yeah, interesting.
Yeah, that's my guess.
Questions? Yeah, please.
I'm just wondering if it's possible to directly learn the unannotated video, because we have so much videos coming directly learn human motion from that. If we can do that, I think the model would be very, very powerful and generalizable.
I agree. That's also my dream. But so do you like? I don't know how to do that, right? I think there are works start to do that, but to really reconstruct or to model human motion. So let's say there are two types of tasks, right? So given a bunch of in the wild videos, one thing people try to do is to reconstruct the motion from those videos. Another thing people try to do is to I'm thinking is to not really to have the explicit 3D reconstruction, but to try to learn some behavior representations from those videos. So I think for given lots of in the wild videos to reconstruct the 3D human motion. Yeah, so far people have been maybe using the 2D annotations, this type of things. But I think language, text descriptions is another way of annotating the information, right? So that probably could be leveraged as another kind of source of annotation, not explicit 2D key point annotation. Yeah. Yeah.
Any questions? Any more questions? Good, then we have
long
That's
break.
actually good. Yeah, we have a coffee break now. We are continuing at 10:40 with signing key and then Alan Newell before we go into the lunch break and focus. Thanks.
Thank you very much.
That's actually an interesting idea, like learning these kind of, video generation models of humans, and then kind of.
That's so sorry. Let me close it.
I also need to kind of.
Yeah, but it doesn't respond to me. Doesn't respond.
Yeah. Okay, I think I will come actually to your workplace to have there's always something. It's very inspiring. I'm actually like, okay, so you have this connection model, you might actually be interested in this 3D right? So you can see, but you don't have access to that, right? In some sense, right? So yeah, I think those are like this.
Yes, of course, but like, I might.
Not now, maybe otherwise.
No, it's okay. It's just yeah.
Okay, so thanks for your talk. There was one thing where you were like having a gradient to generate like collision-free poses. So like, can you try to give an intuition how you get a good gradient to actually get like collision-free? That sounds like the difficult thing to get like a gradient that is useful for that, right?
Yes, so we actually we have a body model. So we have a body model which has a body.
Could you kind of?
I think I see it if I remember correctly. So for every pose, we have a work which you can basically give a query point, which can tell you how much you are in a body, right?
Okay,
With that information, actually, if you
actually take the sign
yes,
to get a gradient.
I'm not sure whether the gradient or the occupancy, but the thing is, once you have such information, volumetric information of your body, and then you have the thin point cloud, and then you can push your body out of it.
Okay.
Yeah, so you can get the gradient.
Okay, that's
Semantic segmentation.
It's post-processed in that case.
So it's I would call it post. Let me close.
You have to leave.
No, but just like this doesn't anyway.
Yeah. So assistant professor at NYU, many foundational works, honorable mention on the Mark Prize, right? So great pleasure to have him. I think also, when we were talking about the spectrum of 3D to fully learning side, I think we are here more on the learning side. So great to have you around, and very much looking forward to your talk. Thank you.
Thank you, Adam. Oh, okay. All right, let's do this. I hope on Zoom people can hear me, right? Okay, cool. Yeah. So in today's talk, I want to just talk about diffusion transformers again. I think I talked about this last year at CVPR at a different workshop, but this is really about diffusion transformers and beyond, right? And there will be some reflections and also some of the follow-up work after diffusion transformers. And I have a small title is why you should stop worrying and love the IT. I'll explain what I mean. Cool. So okay. I think this is okay, good. All right. So if you are not familiar with diffusion transformers, I was before 2022, people start talking about scaling, but really just all the language models in NLP, folks are having all the fun, right? So we have this scaling laws. We are scaling the GPT family for natural language understanding and generation. But in terms of image generation, right? People also try scaling things up, but the scaling behavior is not ideal, right? So this is a plot from the Imagine paper from Google, and you can see if we have this UNAT backbone and UNAT family for diffusion models, and if we just keep scaling up the model size, actually the performance does not really improve much. So one of the problem that we identified is at that time, diffusion models really uses this highly non-standard architectures. This is very different from the NLP domain, right? So in NLP, transformers started dominating everything, and from GPT-3 and Chinchilla, all the scaling laws, people study the scaling behavior using this shared standard architecture, which is transformer. And it's very simple, it's just stacking all the transformer blocks, right? But in contrast, this is what we have for diffusion models. So this is screenshots from the Imagine paper again. It's a UNAT, but it's also not just a standard UNAT from the original paper. It has been involved through the years, and people are adding different customized modules, specific designs. So it becomes really a monstrous architecture that has self-attention inside it. This network, people still call it UNATs, but it's really a highly non-standard architecture. So the key question we wanted to ask is can diffusion model really also benefit from the simple and scalable architectures? Right. So this is why we decided to work on this, and we presented this new architectural family, which is called DIT, which means diffusion transformers. It really represents a new class of diffusion models. And this is some samples from our model. And this is just another a scaling plot where we can compare different sizes of models in this DIT family, from a small model all the way to an extra large model. And this is comparing to the state-of-the-art diffusion models with UNAT backbones. At that time, you can see diffusion transformer architectures is much smaller and much more efficient, but achieves better performance. So how do we do this? I probably will skip this part quickly. This is just covering the diffusion basics. So for diffusion models, if we really need to go over it, it's really about just sample real image X0, and we need to sample some noise Z from a standard Gaussian distribution, and we crop X0 with Z. We can call it XT now, right? And now the goal is to train neural network to predict Z from XT. Okay. And one of the seminal work in this space is, of course, is really about the diffusion model actually having a is done by using you know, a VAE encoder, and then diffusion process will happen by the VAE encoder. Very important thing is about how we actually measure the model complexity, right? So basically, there's a lot of discussions. I think one of the fundamental difference between computer vision or any models that involves kind of like, you know, visual modeling is we cannot fully can just trust the number of parameters. So the idea here is like if you just look at the parameter counts, it's probably not a good measure of complexity. And one of the things that we can look into in this work is flops. So it's pretty good, although it's also not perfect. Okay, so now we can get into this kind of a DIT design. It's actually very, very simple. So again, like if you have the input to the whole system, to the whole neural network, basically a few things, right? You have the input image, you have the forward process time step T, and you have also some of the conditional information, for example, labels, text, etc. And similar to LDM, we'll also have like a VAE encoder, right? This is a you know, giving the diffusion model kind of latent space to work on, and also kind of compress the raw input into something that's much more smaller. So we have this kind of spatial latent, and then we kind of have this forward process, and we need to utilize this forward process time step and get like the noise latent, and then like it will take the embeddings of both the forward time step and also some other conditional information and put them in DIT model. And then like we need to have our objectives, which is noise prediction, or it can have like covariance prediction as well. This is very standard diffusion models. And here, this is how we kind of define the training losses as well. Okay. So now we want to really unpack this model and discuss what exactly is like the diffusion transformer block design. So it's again like very simple, right? So it's the DIT design space is basically a transformer block, right? So as you can see, we have like some MLPs and embedding layers. Not supervised, conditional generation task. C will be class labels, and then we add them together. Now, like this will to the DIT block. Okay, and the details, for example, the petrification is very important. So, like what when working with this kind of like noise latent, it's still a spatial kind of like kind of cubes. So we can actually petrify it and put this into the DIT blocks. So if you think about like the DIT design, one of the key challenges is about how we actually work with this additional conditional information, right? So there are actually a couple of ways to do this. There are like very simple and very basic ways of doing this, following what happened in in NLP. So basically, we can do this in context conditioning, right? This is something extremely simple. We can just like concatenate the additional conditioning information with the image tokens from the petrification of noise latent, and we just concatenate them together, and then like we can construct this kind of like sequence, and then we put this to the next multi-head self-attention layer. Okay, so we call this in context conditioning. You can see the training looks good. We can get like reasonable performance. But of course, we can do something else. For example, we can do the cross attention, which means like now we will use multi-head cross attention layer. This is one kind of additional kind of block between the self-attention and point-wise feed-forward. We can also integrate the additional condition information to the DIT block. This gives us like a slightly better performance as well. And finally, we also, right? So this is, again, not something new. This has been used, and also it has been used in. So here, additional NLP layer that will take the additional conditioning information and then project this into 60-dimension, kind of a gating mechanism in some ways. So here it's called like scale and shift, right? This is basically the affine transformation parameters on top of the layer norm, which is kind of very standard thing. But like because we use this kind of affine transform weights as like additional gating mechanism, and then like this parameters actually predicted from the conditioning information. So this is also a very effective way for us to really integrate this conditioning information to the DIT block. Okay. So if we do this, we can see, yeah, like the model, this ADA-LN variant actually converges a little bit faster, but the performance is not really kind of better. It's slightly better here, but it's not much compared to other options, right? So here we started looking deeper into this kind of design, and we found something, right? So if you are familiar with ResNet and like all this kind of like classic architecture design, and from this paper, this is like very famous paper, accurate large mini batch SGD training image line in 1 hour from FAIR. So there actually they proposed this kind of initialization term. They call it kind of batch normalization, gamma initialization. So basically what it says is basically you want to initialize this gamma to 0 in the last billion layer of each residual block. This actually improves the results for both small and large mini batches. And this has been a kind of pretty useful trick in many cases. So it leads to better optimization behavior, and results can also get better, right? And if you look at the original UNet code from the original the DDPM paper, you can see there's also like one special kind of like design or trick not mentioned in the paper at all, but actually this is super important in practice. This actually makes us to rethink what's the difference between our transformer or DIT design versus the common practice people have been trying in the past. So here, it's the same thing. You can see, we are learning this kind of residual path, right? And then here, it's a kind of residual block. So you have like X plus H. But here, if you initialize the scale to be 0 at the final convolutional block here, right? That really means like you are, kind of like at the initialization, you only have kind of like this highway, this shortcut from the input direct to the output. You are not learning anything. You are not really, kind of like mapping anything on the residual path, okay? So it turns out like this is something, even though it's not mentioned in paper, but empirically it's very important. So I guess like one of the hand-wavy intuition here is like, when you have like really large diffusion time step, the input is almost kind of pure noise, right? So if you think about like diffusion models, like what should the DDPM model do? Probably you should just do the identity mapping, right? Just to do the skip connection, and this can provide an easy path to just like copy paste the DPM's input. So just like some intuitions. But if we can incorporate this kind of like new design, we can see, it's very easy to do this because we can just add additional kind of scale, weights after the multi-headed self-attention block and also the point-wise kind of feed-forward block, right? And we will actually initialize this term to be 0. So that means like, at initialization, you have this shortcut directly from image tokens to the output through the whole network. It turns out this is actually really important. If you run the whole thing with this kind of design and with this kind of better initialization, we can see the ADA-LN design actually yields like much better performance. Okay, so this is like the DIT block design, and I really like this type of like visualization in terms of like implementation. So originally, like for ADM, LDM, UNAP load, right? Because it's kind of a highly non-standard architecture. You just need to write so many kind of different modules and code to do this. But now with this like DIT block, it's just like a few lines of code, and you can achieve even better performance. Okay, so one of the fundamental reasons that we want to study kind of diffusion transformers is really about like scalability. So one kind of design space that we haven't really talked about is this how we get this kind of image tokens from the noise latent, right? So this is also very similar. If you are familiar with vision transformers, this is basically the same idea. Although like now we work on like this kind of like noise latent, which is also kind of a 2D structure. So nothing fancy here. We just need to define the patch size that we have. So if you have like, you know, a large patch size, you'll have fewer tokens, right? If you have a smaller patch size, after doing petrification, you'll have like a longer sequence with more and more input tokens. So this means like we can have this one additional dimension to scale up our model because we can very flexibly control how many vision tokens that we need. So here in our design space, we have like P equals 2, 4, and 8. Okay, and again, like for other model kind of variance design, this is largely follows the DIT model. We have the small model, base model, large model, and X large model, where we vary a number of layers, the hidden size dimension, number of heads, and by doing this, we can have like different G flops, right? Like the model is getting bigger and bigger. Okay, so this is like overall the design space of this architecture. So we have like different block designs, we have different patch size, and we'll also have different model sizes. So for experiments, just like quickly go over it. I think the one sentence summary of this is basically model compute will lead to better generated models. So we can do this by adding more tokens. So this is basically showing within each of the model variant, right? Like from small to X large, you know, like if we increase the number of tokens by decreasing the patch size, we'll have like better and better performance. Of course, we can also scale up the model sizes. So this shows like under the similar kind of patch size, sequence length, if we scale up the model parameters, we can also observe better performance. What's even more interesting is like in diffusion models, we can actually show this viral scaling behavior. So like, again, like we have these 2 dimensions for scaling up. We can have like bigger models with more parameters, or we can have like smaller patch size, which means like longer sequence lengths. So you can see like from the left top corner of this kind of like visualization to the bottom right, the performance is getting increasingly better and better. Okay, there are like more visualizations, you know, across different kind of samples, we observe something very, very similar. Okay, so I think like, you know, I wouldn't call it kind of scaling law, but like we do have this observation, like somewhat compute is all that matters, right? So there's actually a very high correlation between the flops of the model versus basically the image generation quality, like as measured by the FID score, right? It doesn't matter if you just like scale up the model size or scale up the sequence length. You can see this kind of scaling behavior. Again, like this is another plot, and we have like more plots showing different like metrics beyond just FID. So we can see the precision, recall, inception score. They all follow a similar kind of trend. Okay, and another thing is like, you know, basically for diffusion model, it's a very interesting family model, right? Because if you talk like compute, you always have these 2 things. One is like the training compute versus like the sampling compute, because you can flexibly increase the sampling compute by adding more steps. But here we show like sampling compute cannot really compensate for the model compute, right? Basically, you know, with a small model, like however you want to kind of like, you know, sample more steps, it won't really outperform a bigger model with bigger flops. So there are like some more examples. This is all done on ImageNet dataset, trained on 1.2 million images. This is from almost 2 years ago. So there's like at the time we didn't do any text to image general models on this billion scale data set, but we can already see really good quality here. We can do something even more interesting because we have this class embeddings. We can actually have random walk between this class embeddings. And this is how we can show this cool realization of interpolating between different classes in ImageNet. And finally, this is an interesting image I really like. Bill did this. So basically, this is a cool example from original Big GAN paper, and they are trying to generate this dog ball example. But this is after maybe 5 years. This is the sample that we can get. Okay. In terms of quantitative results, we were the state-of-the-art method at the time, and outperforming other LDM variants. So okay, so this concludes the DIT presentation. This is not new content, but then I wanted to really talk about the timeline here, right? So we released the paper 2022 December, and was released on arXiv, and in early 2023 it was rejected by CVPR 2023 due to lack of novelty. At that time I also think, oh, this is a really good model and we shouldn't use UNet anymore. We should just push people to try to use DIT. So I actually, at that time, I just went to NYU, become an assistant professor. So I was in contact with many companies and say, oh, we have this new model. Do you want to try it? People are actually excited about it. But at the end of the day, I think nobody really wants to take the risk and say, oh, DIT seems great, but we'll continue using UNet. There's a huge momentum there. And this is now I want to talk about why you should really stop worrying and love DIT. So the first reason is really just about scalability, right? So after a few months, I think this is September 2023. This is maybe a 9 month after the original DIT paper. So there's one group in China. They released a pretty serious effort in further scaling up DIT model to text-to-image generation. So they call this model PixArt Alpha. It's called fast training of diffusion transformers for photorealistic text-to-image synthesis, right? Basically what they did is they scaled up the original DIT model and tested on the text-to-image generation. So what they observed, which makes a lot of sense, is this great training efficiency, right? They can show only using a fraction of the original training cost of a UNet-based, for example, stable diffusion model. They can get much better performance for this type of text-to-image generation tasks. So I want to talk about this model a little bit more because I think this is actually a very good paper if you want to use diffusion transformers for your own task. So because now we don't have the class condition, we don't have this class labels as our conditioning because we're not working on ImageNet anymore. So you need to text encoder, right? And then remember, in one of our DIT block design, we have this multi-head cross attention between the MLPs and the sub-attention. So basically, they also adopt similar design where they learn the text embeddings using a T5 encoder, and then use a multi-head cross attention to integrate this information, the text conditioning, into the DIT block. Okay, and then everything else is pretty much similar to the original DIT design. But one thing that's critical, and this is something I don't think a lot of people knows or are aware of, is original ADA-LN design has a serious parameter issue, which means because we need to take this MLP layer, which is 6 times the hidden size of the entire neural network, and we need to repeat this for each individual DIT block. Okay, and then at that time, if you only have smaller models, let's see, a few hundred median model, this might be okay. But if you want to scale up your transformers, and now this actually becomes an issue because this part alone will take like 1/3 of the parameters. So imagine like if you are training a 3 billion model, right? 1 billion of the parameters are kind of wasted by this MLP layer doing the ADA-LN conditioning. And what's worse is like before you can justify this because now because in DIT we combine the class labels with the forward time step T together and have this MLP. But in this kind of text to image, okay. So, but in this kind of text to image generation, we don't have the class label anymore. So this MLP is really just about conditioning of the time step T. So literally wasting all the parameters, right? So what they did here is pretty smart. It's just like you do this only once in the beginning of the network. And then you share this, kind of embedding or this projection layer across all the N blocks. So this actually saves all the parameters. Okay, but of course there are like other kind of details, like how do you do conditioning and so on. But I really like this solution. Another kind of important factor here is they show the network can be pre-trained with original DIT weights that we released from ImageNet, but it's actually very, very helpful. And they have like more follow-ups showing like we can do faster sampling, better control, like very high resolution generation, like 4K generation as well. Okay, so this is kind of September 2023. Although like people start noticing diffusion transformers and start like serious effort in scaling things up, but still like the kind of like the majority of the diffusion models are still UNet backbone. And things finally changed earlier this year. In February 2024, OpenAI released this Sora model. Sora is like Bill is the first author of the DIT paper. It was like my intern at FAIR. We did the diffusion transformer together. And Bill joined OpenAI and became a co-lead of Sora. If you read like the Sora technical report, this is basically very similar to the original DIT design. And they also can acknowledge that. So because now you work with videos, so instead of like just have a 2D noise latent, you have the space-time patches. And now you can have like a proper video diffusion model with kind of like a transformer backbone. So in terms of like real scaling, right, this is also something I'm pretty sure like Bill did this because in our original paper, if you remember, we have this kind of real scaling in the 2D space. But in Sora, actually, they also did this kind of real scaling for videos, right? But you can see, kind of similar kind of scaling behavior. Okay, so this is about scalability. Talk about is like, flexibility. So I want to introduce another work. This is called SIT. This is going to upgrade to the original DIT work. And the title of this work is Exploring Flow and Diffusion-Based General Models with Scalable Interpolant Transformers. Yeah, so there's like some kind of like interesting, concept here. For example, interpolants. And this is actually from a paper in 2023. So this is a paper called Stochastic Interpolants, right? It's really just a theoretical framework to bridge any two arbitrary probability density functions exactly in finite time. And also the theoretical contribution also includes kind of unification of flow-based and diffusion-based methods. So one kind of like example under this general framework is you can actually connect kind of Gaussian noise to data distribution, which is basically, for example, the image generation model that we have right now. So like more specifically for the interpolant framework, I think this is kind of like a general thing because for flow and diffusion models, they both utilize this kind of stochastic processes to gradually turn the noise into data, right? And the time-dependent processes can be summarized at this term. This is called like interpolant. So xt will equals kind of alpha t times x star plus sigma t times epsilon, right? And here, alpha t and sigma t, these are like two functions. Alpha t is decreasing function of t, and sigma t is an increasing function of t. So you might have heard about like, rectified flow, flow matching, and so on, right? And basically they are all the same thing. It's kind of crazy around the same times, like September, October 2022. There's like complete kind of independent work from the community, and people are studying something really, really similar. I'll skip some of the details, but I think one of the most important thing of having this kind of like more general framework is basically we can actually relax the rigid definition of SBDM. So basically SBDM actually introduces this noising process, right? And if you think about this, we can recast this as an interpoint. So basically now we have, remember the alpha t and sigma t here, but now like instead of choosing this alpha t, sigma t freely, actually, like this coefficients are determined, this is going to be closed form, but they are determined by the noising process above. And another thing is like this only maps to Gaussian and does so in infinite time, right? So you can see SBDM is actually one but possible interpoints. I'll quickly skip over this, but like we can basically compare diffusion models and flow matching objectives. Because we have the diffusion transformers, we can study all this kind of design decisions and variants in a unified kind of framework with the same kind of backbone. So we can actually compare results. So again, like, there's some theory contributions, but like the things kind of are still kind of remaining on theory level early 2023, but SIT actually further investigates the connections between diffusion and flow models and their kind of performances in this relatively large-scale image generation tasks. We use SIM-DIT design, and our starting point is actually a common like conventional DDPM DIT, and we study kind of 4 key components: the time discretization, model prediction, interpoints, and sampler. Because of this kind of like interpoint framework, everything can be decoupled and everything can be studied kind of like orthogonally, right? Like we don't need to tie everything together. So this actually enables a whole new search space that we can actually play with this image generation tasks. So our final SIT model, like for further details, please take a look at our paper. But our final SIT model is a model with velocity prediction, linear interpoint, and the SD sampling with specific kind of diffusion coefficients. So we can see with this kind of like new model design, SIT can consistently outperform DIT. It also converges much faster, and sometimes almost twice as fast comparing DIT across all the model sizes. And this is samples we can get from SIT. Again, kind of like co-visualization if you care about implementation. So in diffusion models, if you really want to implement this, you will be annoyed by this kind of like massive variance schedules in diffusion, right? But if you only have this kind of linear interpoint in this kind of flow matching framework, this is like 3 or 4 lines of code, and the performance is better. So why not? There are like some future work, but one thing I want to say is like basically flexibility really means more opportunities. And this is only kind of like innate, this is like we made this happen because we are having this kind of like unified architecture of diffusion transformers. Unfortunately, sad story, it was released on archive like January this year, and we just got rejected by CVPR 24. And we were said like, flow matching is not new, diffusion transformer is not new, your results are great, but lack of novelty. We got like really pretty good reviews from ECCV, so fingers crossed. And then, history repeats, right? Like just after a month, Stable Diffusion 3 was announced. And what is Stable Diffusion 3? Actually combines a diffusion transformer architecture and flow matching objective. So I'll skip these details. It's a very interesting kind of like DIT variant for multi-model kind of like information. And one of the kind of major contribution for them is also they have this even larger kind of like exploration with flow matching objectives, similar to our SIT work. So I would say like given this large scale results based on DIT, I think using interpoints or flow matching appears to be the future. And to be honest, I think there's like already a lot of traction now with flow matching. I think it's simpler, it's better. So if you don't know about this, like feel free to check it out. There's like a lot of tutorials online. I know we are running out of time, but like maybe if you can give me 2 minutes, I'll just like quickly go over this final thing. So and I hope this will connect with Alan's talk after this as well. So I think this kind of architectural unification is also something why you should love the IT, because this really enables exploration across different domains. So people are talking about like generative models and representation learning recently, analysis by synthesis. And we have this kind of recent paper, LDAE, deconstructing denoising diffusion models, self-supervised learning. So basically, this is in collaboration with Xinlei, Zhuang, and Timing Affair. But this is basically saying, like, starting from original diffusion transformer baseline, we can actually gradually morph this network into kind of like the very traditional denoising autoencoder, right? And then through the process, we actually identify the key factor for diffusion model to have good kind of representation learning capability is you need to kind of model, do the modeling in kind of lower dimensional latent space in which noise is added. And another thing is like generation quality is right now still uncorrelated with the SSL representation quality. This is something I'm not sure if it's going to hold for the future, but at least this is what we observed. So to summarize, this is kind of a couple of reasons why you should start worrying about the IT, the simplicity, because it really leads to scalability. And also like, because you have the transformer architecture, you can really explore other things like objectives because you have this type of like flexibility. And the third thing is like, because you have the architectural unification, this really enables exploration across different domains. Thank you.
Okay, we have 3 minutes for questions.
Sorry about that. Yeah.
Let me start maybe with one. So you said like one of the final sentences was that actually the representations don't match yet the SSL quality in these generative models.
So yeah, like if I want to elaborate a little bit more, so it basically means like we have to kind of give up on the generation quality to get like good SSL performance, like in terms of like linear probing. So for the best kind of like model here that we studied, right, like you can achieve really, really good representation in terms of quality, achieving like maybe around 65 linear probing results on ImageNet, but FID is horrible. It's like 200 FID or something.
Why do you think is this?
I don't know, like I feel like basically, I think maybe related to the specific kind of design of the diffusion models, or maybe fundamentally, these are two different kind of directions that shouldn't be connected together. I would love to hear more from Alan maybe, but I think this is kind of like really kind of open research question. I know a lot of people are discussing the unification generation and, understanding, but I think there's a lot of things that has to be done.
Nice. More questions? No one? There's two.
Oh, yeah. Hey.
I got one question about the question layer.
Sure.
Did you try without it? Because in other reading that you show, you always have classifier 2, 4, or 8.
Yes.
But did you try without it?
Yeah, it's a great question. So I guess like there's two things from this question. One is like, can you do this directly on the pixel space without doing any kind of like, VE encoding? So this is something that's very challenging for the DIT model. I haven't really seen a lot of kind of good successes in this space. So it seems like the diffusion model will struggle if you directly work on like the patches in the input raw pixel space. But then like for the other question, like without doing any kind of like, patchification, do you mean like maybe a patch size of 1? Is it something which you mean? Yeah, so this can work. But the only downside is like you need to spend more compute because you will have like much longer sequence lengths. So there's actually a paper from Xinlei, I think 2 days ago, and they actually studied this. They call it PIT. I think it's called pixel transformer. Yeah. So you can find like a lot of empirical results from that paper as well. Cool. Oh yeah.
Thanks for your inspiring talk. I have a little question. The PIT is a one-to-one model, but I have a little question. Do you think the PIT is the ideal model for video?
For video, for vision. Yeah, that's a great question. And the answer is like, I don't know, right? Like, of course, I think the diffusion transformer is great because it's really, really simple. And again, like I talk about some of the benefits why you should try to use the ID, but you will never know, you know, if there will be yet another thing in the future. And I'm pretty open to it. Yeah, so hopefully we'll have something new.
Okay, then let's thanks signing again.
Thank you. Thank you.
So this SSL result is actually okay. Okay, good. So it's a great pleasure to introduce our next speaker, Alan Yule, who's a Bloomberg professor at Johns Hopkins University. Not sure how many of you know that he was actually a PhD student of Stephen Hawking, and then since then transitioning into AI and really shaping the field in many ways over the last decades, winning all prizes that our community actually awards. So yeah, very much looking forward to your talk, Alan.
Okay, well, Adam, thanks very much, and thank you for coming here. So analysis by synthesis, Sanning mentioned words in the last few minutes. So this is an old idea, and I think somebody said recently that the CVPR papers, typical CVPR papers only cite papers about 2 years ago. So I'm proud in this talk to cite papers that even one of which dates back to the 1970s. So the idea of analysis by synthesis is perhaps that you should think of vision as being inverse computer graphics. There is a 3D or 4D world out there. The task of vision or image understanding is to estimate the 3D properties of the world and perform a whole series of tasks after that. So there is a type of duality between models that can generate images, or synthesis, as I called here, and models that can understand images, in this case, analysis. So I think the first person to articulate this was Alf Grenander in 1976. I think he wrote about it earlier, and it can be expressed as Bayesian inference. It's out of fashion. I'm not sure it ever really was in fashion, but in my long experience of computer vision, the things that are out of fashion usually come back into fashion sooner or later. And there are a lot of very good ideas in the past that are forgotten, some deservedly, but a lot of them, I think, can lead to big improvements. So from Pavan Singer over there on the left, you see a cube, you see an image, 2D image of a cube, and everyone sees it's a cube. Why? Not because we've trained deep networks to estimate it's a cube, but we have constraints, generative constraints, synthesis constraints of how a cube could be projected to form the image. Now, that doesn't mean that the image should be understood as being a cube, because there are many things that could have generated exactly that same image. But then we have prior knowledge about the world that cubes are more likely than anything else. So interpret, so we use a combination of the generative process, the likelihood, and the prior to interpret it. There are really nice illustrations of this. My colleague, friend Dan Kirsten had illustrations of a ball in a box. This is visual perception. And in fact, the motion of the ball depends entirely on the motion. The perceived motion of the ball depends on the motion of the shadow. The ball does the same thing in various sequences. The shadow does something different. And from analyzing the shadow, just from varying the shadow, you can get the ball to travel along the surface or to go upwards. This is just to suggest that humans have sort of do some form of analysis by synthesis. You have prior knowledge about it. If the shadow moves, the ball, there's got to be some reason for it. One reason is the ball moves upwards. So there's lots of experiments about this, so lots of visual phenomena that you can use. You can sort of describe, admittedly sometimes in a hand-wavy manner, by assuming that vision is Bayesian inference with generative models and trying to interpret the world inversely. I should say, when all this was being done, basic ideas came out. Computer graphics was very primitive. There was a conspiracy theory that the Apollo landings in the 1960s never happened, that they were all simulated by computer graphics. But anyone who knows the state of the art of computer graphics, even 20 years later, knows it would be a lot harder to have simulated the moon landings than to have actually sent people to the moon. So computer graphics barely existed here. Diffusion models were never thought of. Autoencoders did exist as a very simple neural networky manner of doing principal component analysis, but that's about all. So analysis by synthesis, and actually this does get, I think, possibly to an answer to one of Saning's questions at the end. So they're dual to each other. So if you have a world, and this is for a paper from myself and Dan Kirsten, 2006, just a thought experiment world, you have a world that's where the generative models are really simple, like A. In that case, generative models, very simple, means that the inverse process of analyzing the image can be simple too. So you make the images more complex, B, okay, more complex generative model, more complex generative word, and so the analysis becomes harder. And then you move over to the right, which was essentially a capture type of image in number C. I think captures weren't even popular at the time. You generate a very complex image, and so the process of going from the image to interpreting it, the analysis becomes harder. So in principle, analysis by synthesis, as conjectured for the brain and as a promising way to do computer vision, says that the two processes are dual to each other. But then, do we actually need good synthesis in order to do good analysis? People who spend a lot of time making really good synthesis models of diffusion models or computer graphics models, they are evaluated by FID scores and things and how well they generate the image. So you should think that if you believe in analysis by synthesis, the more realistic the synthesis, the better the analysis. But if our goal is analysis, we only need synthesis algorithms that are good enough to be able to form the visual task that we want to do. So maybe if we just want to classify ImageNet, then hey, it doesn't, we don't need a really strong diffusion model to generate those images, because frankly, classifying ImageNet is not hard. Human vision, your visual systems do much harder tasks every few minutes. So a few visual tasks may require very good synthesis, but many do not. And the ones that may require very good synthesis are not ones that the computer vision community works on, because we don't have annotated data sets to evaluate our performance. And also, if you are, like myself, influenced by human perception, people have said, okay, you carry priors of objects in your mind, and you have perhaps a virtual simulator, which means you can imagine everything in the future. Josh Tenenbaum at MIT is very eloquent at saying this, but think about it for a moment. If humans have the ability to do analysis by synthesis with really accurate synthesis models, then if you simply close your eyes, you could imagine this whole scene and generate it, and I bet none of you can. You know, we can imagine things, we can dream about the world, we have that sort of capability, but it's probably not terribly accurate. Possibly a few people like architects, my father was an architect, you know, film designers might have that ability, but most people don't. So the take-home message here is that, you know, how good do we really need to be able to generate images in order to analyze it? And so here we can take a pragmatic approach and say, well, we don't need the generative models to be really accurate. We just need them to be good enough for the task. And that's partly an excuse because of the work I'm going to present here, a lot of it done, or actually all of it done, I think, in collaboration with Adam Kortulewski, uses a rather simplified generative model. So I'm giving the excuse for not using a more realistic one. Okay, going back, again, it may be unfashionable in vision to believe that the world is 3D or 4D, and that to address it, to model it, you need to have three-dimensional models of objects and 4D to take into account their spatial properties. Of course, in computer vision, we do this for humans. You know, you can hear talks by Michael Black and so on. And we do it for humans because we got annotated data to do it. So we are, you know, we're sensible enough to do it. We don't do it for other objects, mostly simply because we don't have the annotator to do it. And we are somewhat slaves of the annotated data sets that we have. So going back to the 1980s, which was a wonderful time because people could come up with lots of conjectures and nobody had to validate them on any data set at all. So there was a lot of nice imagination. There was a theory of Miederman called geons that you represented objects in terms of elementary components called geons, and the objects were just combined together out of these elementary components. So you had a 3D model, and then the important aspect of the geons was it was compositional. The model, the object was made out of these components combined together. So this was 1987, and to get my earliest reference, you can say this sort of idea was also in David Marr's book in 1982, but the first person to do it was somebody called Tom Binford, which I'm not sure anyone has heard of. No? Oh, one or two. Well, perhaps best known as these days as Jitendra Malik's PhD advisor. But Tom Binford was one of the true pioneers of computer vision. It's a pity his contributions aren't quite so well known. So, okay, so if you want to do analysis by synthesis, or you really focus on the analysis, you'd like to have three-dimensional models of the object, and you might make them compositional. And so we have papers here which I'll generally call 3D compositional generative networks, 3D CGNs, sometimes called neural mesh models. The titles changed a little bit in the papers, and frankly, a precursor why that happens is one of Sunning's other presentations about papers being rejected for lack of novelty. And so this is, frankly, a bit ridiculous to my mind, because if people rejected papers for lack of novelty, AlexNet should have been rejected because the basic architecture who was there, somebody had even won a prize for it, you know, a few years earlier. And it was just a small tweak on other things that were there. Not to disparage ImageNet, obviously getting it to work, not to disparage AlexNet, getting it to work on ImageNet was incredibly impressive, and nobody in their right mind would imagine that you should reject that paper for lack of novelty. But if you follow many of the experience of Sanning and others, this happens. Perhaps never to Jeff Hinton, but to lesser mortals, it happens very frequently. Anyway, sorry, that's a little bit of a diversion, but we've got three-dimensional compositional generative networks. So they're three-dimensional. The factorization, the generation makes two approximations. First, you're not actually generating the real image at all, you're generating features. And the features are trained in certain ways so that it's fairly straightforward to generate them. And secondly, the generative model is factorizable. So what you generate here is independent of what you generate here, except it's conditioned on being a human. So this is not a very good generative model. You couldn't generate anything really realistic from this. You couldn't get good FID scores, but we don't care because our goal is analysis. And as we say, you may not need really good generative models in order to do good analysis, at least not if you're evaluating your algorithms on the current benchmark data sets that we have. So there's papers here, there's more papers, and there's earlier stuff we did on 2D comp nets, which had a lot of the similar ideas in them. So how well can the 3D CGNs perform analysis? And I'll show a figure about them a little bit later on. And we're going to test them in two types of ways. One way is how well they perform on data that's very similar to data that they're trained on. So this is classic machine learning. You train, you have some training data, you have some test data, and you know what the last 10 years have shown is deep networks do incredibly well on that. Essentially, from my perspective, they're behaving somewhat like intelligent parrots. Intelligent parrots are very good at recognizing stimuli. They could do certain tasks better than doctors because of those abilities, but they're not perhaps the important point of, well, I don't want to be too critical of parrots and who really knows how their brains are working, is that they are not good at generalizing to novel data. And the same thing applies to the previous set, you know, the standard set of deep networks, until possibly you have these enormous trained data sets which have some ability to do it. So you test these algorithms conventionally, where the training and testing data are ID samples from the same underlying distribution, but you can also test them in out of distribution settings where you ask them to do tasks that they have not been particularly trained for and on data that they're not particularly trained to do. So these models, to train them, requires 3D annotation. At least there may be clever ways to do it that we haven't thought of, but essentially you need 3D annotation for this, and you need 3D annotation for testing them as well. Now, this goes against certain of the bigger current popular themes at the moment as you try and see what you can do with lots of data that is hardly annotated at all. And there's a lot of progress you can make with that. But I believe, you know, the cycle will turn and we'll realize, as well as that data, we need to have data with 3D annotation, 4D annotation, if only for evaluating whether our algorithms are any good, and probably for training them. This, however, put restrictions on what we can do. So we worked on the Pascal 3D Plus data set because that existed. People at Stanford had made it, and we could use it for training and testing. Although more recently, I'll mention at the end, we've scaled this up a lot. So for out of distribution, what we do is we can test to see if the algorithms are robust to occluders by photoshopping occluders and putting them in them by the OOD CV data set that we created, and I'll show in a minute, and on realistic synthetic data that I'll say later on how we generate it. Realistic synthetic data meaning, okay, diffusion data, but diffusion data prompted with 3D. Okay, so here is sort of one figure of what these CGNs can do. You have an input image, in this case of a car. You have a 3D model of cars, of buses, of airplanes, whatever else the object is. For that, for each object, you have a generative model, a 3D CGN of how it can generate feature vectors at different parts of the object. And then you can do what was called render and compare, which essentially is analysis by synthesis. The sort of dumbest way of doing this is that you consider every possible object that could have generated the data. You estimate, you have an algorithm that tries to estimate its 3D pose that generates it best, and then you consider you interpret the image as being the object that is best at generating the data with the pose that generates the data for data best as well. Okay, so generative models and feature vectors, and the feature vectors would be vertices of CAD models type, for that type of representation. The 3D pose, the object class, are known during testing, during training. Now, making another point here, we are not training the algorithms to do classification or 3D pose estimation at all. We actually train the algorithms to distinguish between different vertices of the same object and vertices of other objects. So it's trained to do one task, but then it's able to do other tasks, object classification and 3D pose estimation as well. The inference, render, and compare, you can do it. We came up with other methods that are faster, at least for classification, about the speed as a standard deep network. Okay, so to show people tables, which is what you expect at a CVPR conference, here are some of them. This is the performance of the 3D CGNN compared to the others. The first column is, okay, regular data, regular testing, IAD setting, L1, occlusion, 20 to 40%, L2, 40 to 60%, L3, 60 to 80%. And you can see how much more robust and reliable these algorithms are when the occlusion becomes medium to extreme. This example here of the car occluded by a gigantic cat is a bit extreme, but I was told by my students we actually do get the 3 pose and we estimate the cat from that. So these models, because of their knowledge of the 3D geometry of objects, have the ability to transfer as well, and generalize. Another example of OOD, you take images here from Pascal, you now go into shape, 3D pose, texture, etc. Unusual cases. This was the data set that we had, and you see there's a huge performance drop. Okay. Now, if you do the 3D CGNNs, again, because of the knowledge of the 3D structure of the objects, and other properties, their performance decreases, but not by nearly as much. All these figures are really a bit old, out of date. I think our algorithms and actually the alternative algorithms will probably do better, but the basic picture stays the same. So the 3D CGNs summary, this works for 12 object classes on Pascal 3D+. There was effective as state-of-the-art alternatives when tested. IAD setting, they're much more robust when tested on new domains in the presence of occlusion on synthetic data. And this can be improved by extra things you can do, which again exploit compositionality by Prakar Kaushik et al. Okay, so this is okay, but maybe in computer vision, you don't really care about 12 objects, right? You care about more. Can you scale it up? So the issue then is this relies on data. Where do we get the data? Okay, so how do you get data sets? So there are 2 sources that we've developed, one of which does rely on diffusion models, which of course everybody knows. What we did though is diffusion models are wonderful at generating data, but they don't come with annotations, at least not yet. People would like to get them out, but they're not there. The diffusion models have some knowledge of 3D, but it's sort of implicit and not easy to get to. So I'll present a little bit of work that we had in ICLR, whereby combining the diffusion models with 3D CAD models, you can generate data that's rather nice, fairly realistic, and has 3D annotations on it as well. That's one thing. The second one is a recent data set with 3D annotations of 200 object classes submitted somewhere. Okay, so diffusion models are impressive. Many of them, particularly Sunning's work, to embarrass him. But, you know, they are incredible. They're very nice, very realistic. As I said earlier, maybe you don't need them to be realistic if your purpose is to use them for analysis. But what you do need them is you need them to have 3D annotations in order for training. So you want synthetic data for 3D tasks. You can do a certain computer graphics models that exist already, but diffusion models have the nice property that, you know, they're incredibly rich, you know, enormous data sets, and they can look more realistic than many of the synthetic data. So here is the basic idea. Very simply, you have a computer graphics model, you have a diffusion model with prompt generation. You can put them in there. Sorry, we're using units within the diffusion model. But you know, that could be changed. You produce large amounts of fairly realistic data with 3D annotations, which you can use for training algorithms as well. So this is an attempt, a way of generating the, you know, of missing the data gap. You know, as I say, I believe the world is, you know, believe the objects in the world are 3D. I think computer vision needs annotations of that. We don't have it. They have to be created. All the evidence about human perception that I'm very much influenced by really implies that humans have 3D knowledge of objects. And we learn that during development by interacting with the world, touching objects, playing with them, things like that. So we learn it from multimodal sources, but we have that type of knowledge. Computer vision tends not to have it, except for humans, because we've got data for that. And anyone who's sensible working on working with humans is going to use three-dimensional models for humans. Okay, so we should be doing it for everything else. Okay, so this means, though, that if we believe in this type of approach, which I do because of the many properties, the robustness, the ability to get information out that you could use for robotics and other things, you have to create this data, and then you have to show that we can scale up the algorithms. So given this data, we can scale up the 3D CGNNs. There's some technical issues about what we did in them. They were trained, if you remember, to distinguish between different vertices. The number of vertices to distinguish between is going to scale roughly quadratically with the total number of object classes. That is a lot. You want to avoid doing that. And so we developed a method called compositional contrastive learning, which essentially reduces that by starting to remove vertices between object classes which are not confused. So then you scale this up to 116 object classes. That's work in progress, you know, in review somewhere. Why 116? Well, because it depended on the data sets that we were constructing at the same time, and they weren't, although they're 200 classes, they weren't ready enough at the time we had to submit the paper. So the findings still remain that these 3D CGNs are more effective against standard types of deep networks by about 5 AP. You can do more complex things with deep networks that would increase that, but you could have done that with our algorithms too. Now, this may be a little bit surprising, but the point of view here would be that our algorithms know about 3D data. They're trained to use 3D data, whereas standard deep networks, however clever they are, don't know about 3D data, even if they're given it to train on. And the classification performance increases as you increase the amount of occlusion on these objects. And so you're outperforming them by 10 AP, etc. Okay, and if you do it to synthetic data, again, you're outperforming the alternatives. Novum is actually an earlier version of our work, etc. So there's the conclusion. So I'm arguing for an old idea that's out of fashion, but maybe coming back into fashion again, because there's so many people working on nice generative models of images. But I'm making the point that good analysis may not necessarily require good realistic synthesis. You know, it depends on the task that you want to do. And computer vision is basically doing pretty coarse tasks at the moment. Maybe you need accurate, very accurate generative models to distinguish between my car when it is dirty on a, you know, and my car when it isn't dirty, but we're not doing that yet. So then the 3D CGNNs perform well for object classification and 3D pose estimation when tested IID, you know, about 5, you know, and particularly when tested OID, they do require the data for 3D annotations. So we were originally restricted to doing it for 12 object classes, but now we can do it for 100 and probably 200 by now as well. So the series of papers with this, I'd say, yeah, Adam has been a collaborator on all this work. And I guess this is the, you know, the purposes here are generative and analysis, two sides of the same coin, having annotated data sets rather than relying on huge unannotated or weakly annotated data sets. Frankly, I think you need to have it, not necessarily for learning, but certainly for evaluation. And that's a huge gap, I think, in computer vision community. So thank you for listening. Here is the, yeah, so this is the summary slide. I'm down to 1 second or so, so I won't say any more, but I welcome any questions and feedback.
Okay, thank you. Any questions? I mean, I could start with one. I mean, we're discussing this very frequently, so there are not many questions that we haven't discussed yet. But what do we do with things that are not objects? Like when you go into the jungle and there is like so much stuff that is not like this kind of closed form object.
I think we'll cross that bridge when we come to it. I mean, I think there's the issue of how much data you need to learn these objects from. So certainly here we required synthetic, you know, you required enough annotated data to learn the models. I think with insights, perhaps from computer graphics, Gaussian splattering methods, it may well be possible to learn these with far fewer images. If you're walking through the jungle, you've also got, you know, you've got image sequences, you've got the ability to estimate the 3D structure of the scene. Anyway, 3D structure is sort of, you know, compute the structure for motion, binocular stereo, you've got all that ability. Going back to David Marta, quote old references, you got the ability to get 3D out from a single, you know, from a very small number of images. It's obviously not used for that purpose much in computer vision, but you've got that ability. So I'm not, you know, I can imagine that you could construct a model of an object on the fly just from a few images without much prior knowledge about it. Okay.
More questions? Yeah.
Yeah, I just want to hear your thoughts about you know, the role of language in the analysis. Do you think it's necessary? Do you think we should, you know, we get rid of it? Or what's your thoughts?
Okay, yeah, thanks for that question. I think that language is important because language gives us knowledge about objects and about the world. So vision you know, again, partly from a cognitive science human perspective on it, we've got images, there's a vision process of estimating objects, but then there's a lot of common sense knowledge we have about images, about scenes, about object properties, and large language models are an incredibly good way of taking advantage of that type of knowledge. Before that, we had nothing, you know, nothing equivalent. So we certainly need to combine vision with, you know, with language, in my opinion. The question is, how do you do it? If you take existing, very popular, you know, vision language models, and they're throwing all that stuff together, is that the right way to do it? It's obviously very popular, and some people, I've seen a comment saying, okay, vision is solved because of some version of this from DeepMind a few years ago. I think it's good, but I don't feel it's adequate to deal with the really hard vision problems. I think you're hallucinating things. We have some examples on this which are published in this conference, which we didn't put in the critical side, but I got the student to, you know, to do it afterwards. The model will work. It will give you incredibly nice answers to questions about images, but then you find you can generate images quite easily where they give you the same answers, and the answers ought to be very different. So I think language is really important, but for myself, I think it ought to be, you know, I'd like it to be combined with vision in a rather more modular method, to use another term that's almost completely out of fashion. Do it at the object level, maybe at the scene level. Otherwise, the vision is using the language as a type of crutch. I mean, I did like your work about, you know, okay, you're trying to find a coffee cup, so you search for a table, right? That's a good use of it. But anyway, that's a viewpoint.
That the newer models have some bias and also some hallucinations. If you use the generated data to train your downstream model, well, the downstream effect to bring some bad effects on the downstream model, and so how to avoid that?
Right. No, it's good points there. You have to make sure that the generative models could do with everything, you know, are really good generative models, and they could generate anything any real image that could occur in reality. And some of them, you know, maybe some of them do. We found with the diffusion models, okay, they're trained on who knows gazillions of images. They're not very good, as far as we can tell, of generating a guitar scene from a side view. Because of all the data sets they've got, they're still internet images. These are somewhat biased. They don't have it. So, and that would apply to even, you know, to ImageNet data sets. These are biased too. And so there is, and this is a good thing for the community, I hope, not just us. We have to go outside. We have to get all types of images we can, you know, with cell phones attached to our heads or to other people's heads, or to babies, as some people do. And you have to make sure that we can generate anything that exists in the world, I think. Yeah. Otherwise, yeah, the things will be biased. They will not attend. But that's actually a bigger picture of the generative models. You really want generative, you know, you want to say, okay, we've got an analysis process, we've got a generative process. The generative process that we have in our model should be able to generate anything. And if it can't, we need to change it. That means you have to be able to evaluate whether we can generate a particular image or not, which autoencoders is one potential strategy for.
Okay, and with this, we're actually ending on time our first session. So thanks again to all speakers, and so poster session starts at 12:30. Make sure to be there, and then back at 2 p.m. here.
Okay.
Nice talk.
Well, I hope so. Yeah, we lost a few people, but
Well, yeah, but not so much time.
Yeah.
Hi.
Yeah, nice work. I'm one question about 3D like the CGI for like some for like scalability like compared to the science Dr. Science work.
So let's get started with the second part of our workshop. Super happy to have Jiajun Wu with us, assistant professor from Stanford, very well known for his work during his PhD with Josh, and of course work that happened afterwards. Numerous awards, career awards, young investigator awards, and he's going to tell us about generating objects and scenes and worlds. Very excited to have you here. Thanks for coming.
Thank you. Thank you. Thanks for having me here. Well, this is a lot of people. Okay, disclaimer. I have a few talks, but then this one has quite significant overlap with one talk that I gave in the morning. It's not that many people though. So, but other than that, it shouldn't be any overlap with other talks. So if you're there in the morning, this compositional 3D stuff, then you may want to leave right now. Okay. Okay. So yeah, I'm going to talk about generating, generation is exciting, right? So, how can we generate 3D objects and scenes, and how can we go further into generate a world? And a large part of it is, I would say, how can we leveraging the compositional structures or the causal structures of the world? And the reason we want to do that is, as I put the second line here, what it means for computer vision, because, if we can just generate a lot of scenes and videos, and that's
It sometimes happens.
Yeah.
It might get
okay. Okay, I'll just try to speak louder. I heard this is a common issue. So, if you can generate a lot of beautiful videos and scenes and does it work? Okay.
Yeah.
Yeah, if you can generate beautiful images and videos and shapes and scenes, right? So, but how does that have anything to do with computer vision, right? Because the definition of computer vision has become really broad, and everything is out. Generative AI is computer vision. Well, that's probably not traditional computer vision. That's more like graphics, right? But now I guess computer vision is everything. But if we look at this workshop, I think we're still caring about what is real computer vision, in the sense that how you can have these generative priors and how these priors may be useful if you want to solve actual computer vision problems. So I would say, to better solve these problems, you probably do want to think about the compositional causal structures, generation process as well. So you're generating things not just because they're beautiful, not just because they're realistic, not just because they're diverse, but also because they capture the causal structures, and that's why how they can be used when you want to solve computer vision problems. Okay, so what does that mean? I have 30 minutes, right?
yes.
Yeah, okay. So, you have a picture, right? You want to generate that picture. But then let's think about why the picture is the way it is, right? If you look at its image formation process, then the question is, how does nature generate this picture, right? So when computers generate a picture, let's look at how nature is generating this picture. And the picture is because there are just underlying geometry, objects, and textures, right? The world is made of objects, and every object, this line had this particular shape of certain materials. It may move in a particular way, right? So all these underlying physical properties is sort of decide, okay, nature is doing the rendering process for you. So of course you get this picture for free. And people have been trying to replicate that, right? You replicate it in computer graphics. When you build a graphics engine, what you want to do is exactly, you can take all these physical properties and produce the picture. And in the context of this workshop, right, and also I think a more traditional definition of computer vision is you want to invert the process, right? That's why people say computer vision is inverse graphics, because what you want to do in computer vision is sort of try to de-render this process and take a picture that you want to get, what's the underlying geometry or material motion of the objects. And ideally, because there's ambiguity, right? Vision always kind of under constrained process, the inversion process. So you want to not only model a single output, but you want to also have a distribution of these things, right? How can I go from image and try to model the distribution of possible underlying geometry, materials, and motion, all these things from the image? So how can we do that? We have learned that data is extremely powerful. You probably want to scale up if you can have data, right? But unfortunately, unlike images and videos and language, which you actually do have a lot of data for free, for a lot of things that we care about, targets of computer vision, even the intermediate representations, you just don't have data, right? How much data can I have for the 3D shape of the line? I'll probably have like very, very few, right? Even for general objects, any 3D objects, you may have like 10 million as in objects, but for a specific object, you just have very little, and material, almost zero. So maybe we can say, why don't we just collect label, right? So we try to scale up and collect data, and so that's what people have been doing, annotating 2D, and trying to entertain 3D as well, and then doing mocap where you can get geometry and motions of animals and humans as well. Apparently, you have a lot of issues. One is it's hard and expensive, tedious. Second is it's really hard to scale to the real world in the wild data. Right, the mocap studio is hard to build. They're all coming in this giant sphere. It's expensive. How can you capture all these possible things that happens in the wild data? And as I said earlier, we care about the causal structure. What will happen if I move the camera? What will happen if I change the light? That's not possible to do if you just collect data. So naturally, what we say is that possible for us to learn in the wild, right? So if we look at all these videos, and that's great. You have all these diversities. And if we can learn just from these videos in a self-supervised or unsupervised way, that's better. That's great. But as we said, these videos are unannotated. I see beautiful videos of cats moving, but I don't know what's the underlying geometry and materials. I can have a guess. I don't have ground truth annotations. So what should we do? We can have this generative model, right? A generative model of computer vision. Now we want to solve the computer vision problems and want to incorporate generative model inside. So what we can do is we can de-render the world into things we care about, like shape and materials. And then we can re-render them, or we can have a generative model. We can take these intrinsics and re-render, reconstruct a picture. And of course, I can have a reconstruction loss. Ideally, all these things can be done in a self-supervised way, so that I can just use the reconstruction loss, which requires little or zero annotations. I just learn it for free. On top of that, right, the things we choose are not random. It's not like, okay, I choose like 5 different random properties because I care about it. Right, I choose these properties because these are also just examples, but they're like the fundamental physics or physical property in physics that's basically deciding, okay, why the world is behaving the way it is. That's how people design graphics in them, because I know if there's a surface and if it's light, then I can write a reflectance function, right? So there's, all these BRDF functions, for example, they're kind of approximate how the real life physics works. So in that sense, these things are not chosen randomly. These things are chosen because they actually bring in, inductive biases themselves. And also, sometimes you may have even additional knowledge, domain knowledge, whatever, on specific parts of them. Oh, maybe this thing can have, a little bit of a prior that I can try to incorporate. Okay, so that's kind of a whole high-level overview of one approach that we're trying to do, and there's a second approach which I'll introduce later. But before that, this is like the high-level overview type style 1 approach, ideal 1 approach. If you were at my talk yesterday, I would say this is category 1 that you try to put structures inside the system and how generative models can be used in inversion of problems. And what it can do is, you're trying to do self-supervised learning or mostly self-supervised learning on collection data during training, and during testing, just take a single image or a single video, you de-render it to get the things you care about. Okay, so now I'm going to give us some specific examples about how we're doing that. Okay, first look at single object case. Single object, and also I assume it's just rigid. Okay, so there's no parts. And object, the things I care about here is geometry, texture, material, lighting, camera parameters, right? Okay, so as I said, object intrinsics, they may vary in different inductive biases, right? So, for example, if you have an image of a vase, then the way the way it is because there has underlying geometry, surface normals, the textures, which is the beetle, the material, which is how it reflects light, and some lighting components, diffuse specular maps, as well as the environment lighting conditions. Okay, so these are, for example, the object intrinsics I care about. Right. Of course, they're different, and we have some priors about, okay, how these things should be composed in graphics and to produce the pictures, and how these things may be used in a newer renderer as well used. Again, the renderer can be a graphics engine, can be a newer renderer, right? It can be differentiable graphics engines. So, but neural networks using them in a graphics or physics-based way to compose these as well. But on top of that, we have additional knowledge. For example, in this particular case, we know that vases are like rotational symmetric, right? So we have this additional prior about, okay, there's certain assumptions that you can make about the geometry or the surface normals of the objects. We also know that the material of the object, we can make a relatively safe assumption that this thing is homogeneous, right? So every point on object is reflecting the light in the same way, right? So what does it mean is, okay, you can use the same parameterization for the material properties of objects everywhere, right? Because you assume it's homogeneous, every point is reflecting in the same way. You can use the same BRDF function and all these things. So you can make pretty explicit assumptions about some of these properties like normals and geometry and materials. For a beetle, it's a little tricky, right? If you look at the texture of this object, you're like, okay, it's not like every point on the vase is the same color. It's not like a pure color vase at this place, and this point is white and that point is white or stuff like that. right? But it does look kind of, perceptually similar, right? Even if there are specular regions, like this place is really highly specular, I know that underlying color, the actual color of the base, it should be like similar with even these kind of darker regions. So if you look at albedo maps, all the patches should look kind of similar to humans and hopefully also to machines as well. Right, so you can make like an implicit assumption about, okay, what you know about albedo, although it's hard to really write it down as an equation like being forced. So these are like different types of inductive biases or structures that you do have, when you look at specific problems, and how can we leverage these biases on top of the inherent structures among these properties themselves for better object understanding and decomposition. So, because I think this, the work I'm presenting here is a bit old, so I'll now try to I think the idea is still really interesting and directly connects to a lot of more recent work that we have been doing. But I'll just talk about it at a relatively high level because many of you may have seen this paper or have me talk about this paper. So this work is done by Elliot Wu, who did a PhD at VGG with Andrew Fidelity here, and doing a postdoc with me right now. And so he did this beautiful work. If you don't know, I have a slides for it, but I'm not going to show it because I don't have time. But he did this beautiful work on how you can use reflectional symmetry to do 3D face reconstruction without supervision, which won Best Paper Award at CVPR 2020. So you look forward to you're welcome to take a look. But then after that, he went to Google to do an internship while I was at Google. So with Noah, Andrew, and a bunch of other people, we're like, okay, is it possible for us to extend the work? Right. So back then he was using reflectional symmetry to do 3D face reconstruction without supervision. But what we can do here is, okay, is it possible for us to enforce these additional constraints that we may have about the surface normals, about the materials of the objects, and maybe some implicit assumptions about albedo of the object, so that we can use them as constraints into this still end-to-end neural network, right? The renderer part. Once we can do that, what we can do is we can re-render the scene, and we can produce the pictures in novel different views, and we can rely on the objects because of the auto-modeling effectiveness. But the key here is, the re-rendering is, again, neural network, kind of neural render inspired by graphics engines, but you want to incorporate all these different properties. But then how can you incorporate these properties, right? So you can look at the paper to see more details. But at a high level, I would say, if it's surface normals, and you know that, okay, the object is rotational symmetric, then you can use a specific parameterizations. Okay, you can parameterize it in a certain way so that you can say, okay, the object, maybe I would just have, a vector of different radiuses at different heights, as well as a scalar for the height of the objects. And you can easily parameterize the object in much lower dimensional space. And the same for materials, right? And to enforce implicit constraints like albedos, you will say, okay, if the object, different parts of the albedo should look similar to humans, no matter whether it's from a highly specular region or unspecular region, then it should look similar to machines in the sense that you can have a neural network discriminator, which will force the constraints between these different patches. Okay, so basically you can look at the intrinsics of the properties, and you can look at the properties they have. You can look at how they're connected. You can also look at the features they have so that you can enforce these constraints into the systems, which allows you to, again, train without supervision. You just take a collection of pictures of the bases, train on them, putting some structure inside. And then during testing, you can take a single image, you can de-render into 3D, and you can, so here are some results. So you can take an image, you can de-render into 3D, you get surface normals, albedos, and diffuse specular components, material estimations, and the environment maps, as well as you can turn this picture now into 3D, just doing testing from a single image, including like paintings and stuff, into 3D, you can see it from different views, you can relight it. So I thought this is really cool. And I also thought, here we have this rotational symmetric assumption, right? So how can we enforce that? If the face is reflectional symmetric, then you can flip the face and you will say, okay, the face should look the same if I flip the face. But you can only flip, for example, the geometry. You flip the geometry of the face, it should still look the same, right? Assuming the lighting is constant. And in the case of a rotational symmetry case, we can say we can rotate the object a little bit and it should still look the same because we have this assumption that the object is rotational symmetric, which is great. But yesterday I was saying, when you're putting these constraints into the system and you present this work to humans, and natural question people are like, oh, wait, but you're only working on this particular case of basis, right? Or how can you be more general? Right? It's not like everything is rotational symmetric, which is totally true. So how can you go beyond things that are rotational symmetric, right? Have you heard of a bitter lesson that you make this more inductive bias into your system and it just hurts the work, and then you probably want to just go with more data? Okay, I have some counter arguments to that yesterday, so I'm not going to repeat them here. But I think it's a totally valid question that you don't want to just work on basis, right? So, or you don't want to just work on objects that are rotationally symmetric. So natural objects are much more diverse. And so we went on and we asked the question that is, what is really shared among natural objects? What is really shared among at least, objects from a specific object category, right? So in the case of vases, yeah, maybe they share this particular parameterization. You can parameterize the shape in a certain way, make learning problem much easier. But that's not the case for any other object categories or most other object categories. So what is really shared for any object categories? If I look at particular category of objects, I know, okay, they're sharing this. So here's an example, right? So I have this, a bouquet of a lot of objects here, they're roses. We know they're roses, they're, different, I know they have the same name. There's a reason we give them the same name. We say this is a rose, that is a rose. They must mean something, right? And so if we look at just examples of these objects, we're like, okay, what are these roses? And realize, okay, these are just like, multiple instances of the same object category, right? So there's one rose, two. So what is really shared among these roses? And the entire picture is like, you have these, 20, 50 different instances of roses. So I argue that, the reason we give them same name and the reason that they're sharing something, what they're really sharing is not a specific parameterization that shape is rotationally symmetric. But instead, it is the fact that they do share the same distribution of the intrinsics themselves, right? So what are really shared among these roses from the instances is, they actually have, they're named roses because they share the underlying distribution of the intrinsics, the things we care about, They must have an underlying distribution of possible geometry and textures and materials, so you can sample from it. And once you can sample from it, you can put them in the different lighting conditions and poses. You get all these examples, right? So here you're making an important assumption. The assumption is so weak. That is, you're not like, oh, object has to be symmetric, object has to be rotational symmetric. It is not anything that is, it's easy to parameterize it, or anything that you can write down as equations. Or you can still write some equations, but it's kind of very high level guidance, which is sort of instruct you how you should design your neural network, how these different intermediate representation should be connected. Of course, it's closely tied to computer graphics, but you really want to learn. And there's a prior that is, okay, if you have this object category, so say there's a rose and just give you a single image, which is very minimal observations, we already give you so many instances about, okay, what is rose could be about? So how can we go from this, very minimal information to learn the prior that is really shared by all these different instances, which is the distribution, the underlying distribution of their intrinsics, right? That's the generative model we're using. And once you can do that, naturally you can solve this inverse problem of computer vision. And we can solve a lot of computer vision problems. We can solve 3D reconstruction. We solve non-obvious synthesis. We can solve relighting and stuff like that. Okay, so again, don't have that much time. So high level, I would say you can learn the distribution of object intrinsics. You can sample after what we want to learn is you can sample, go from a noise, right? You can sample instances of objects of different shapes and albedos. You're also trying to approximate, or this can be learned as well. But I think in this work we have some other good heuristics that you can have some distribution of the extrinsics, which is the lighting parameters and object poles, right? Just the poles of object. Once you have that, you can put the object in the right pose, and you have the shading. You can put albedo on it, you have the appearance, and you put cameras on it, and you get a fake picture, right? The generated picture of the roses. You can compare that with real observations, real instance of roses. And back then, because this work was like almost 1.5 years ago, we're like, okay, diffusion is not as popular yet. We're like, okay, we can just use again, right, to classify this input image, whether it's a real image or it's a fake image, right? With very minimal, there's, again, nothing is pre-trained, right? I don't have a pre-trained model. I'm not using the diffusion part, which is pre-trained. Everything is just done on this single image. From a single image, when you have this kind of a little bit, very minimal guidance on the inductive biases you have, how the object should be generated, I can construct a system. I can learn from a single image. And what I can do is I think we can do a lot from very minimal input. That is, from that single image, we can actually learn and disentangle a distribution of object geometry and textures and materials. And you can sample from it so that you can get roses of different viewpoints. As in the bottom row, you can see them in the different lighting conditions as a second to the bottom row. And because you're learning a generative model, you can sample different instances of roses, a different geometry or different textures. That's in the middle row. Right. So this is done by Andrew, one of my PhD students. Okay. So of course, now you learn this generative model, you can use that to solve computer vision problems. Right? You solve a lot of computer vision problems. Novel synthesis, relighting synthesis. Here's some more results. Right? All this from a single image without pre-training. You can get a lot just from a single image. Okay, so the results here I think are great if you just look at a single image case, but they're not as perfect as you can imagine for a number of reasons, right? So one of them is we really want to do everything from a single image. There's no prior, right? So of course we can do much better now if you have incorporate some diffusion prior, which has learned very good priors about what natural images look like, right? So incorporate diffusion priors just will work much better and stuff like that. So there's still also a lot of advances in neural rendering in the sense that, okay, what would be the representations? Because I wasn't able to talk about the details, right? Oh, how do you really parameterize the shape? How would you parameterize these the materials and stuff? I think there are a lot of advances in recent neural rendering that will help us to do better as well. But I think the overall concept is the same, right? You build these generative models about objects and think about, these, but the generative model itself already takes as input or intermediate representations. That's exactly the target of computer vision. An intermediate representation you want to get, or the final output a computer vision system would like to get. So they really can help each other. Okay, so I'm going to talk relatively quickly about the other parts, about how we can move beyond from a single object case to transform. So Elliot has been, the person who did this phase paper, before that, the phase paper. And then, as I said, he graduated from BGG and came here to do a postdoc with me. And then we did this collaborative work with Andrea on how we can go beyond, just learning from a single object category, right? We said, okay, we have been doing work on roses or vases, or these are great. And, you can make some assumptions about specific object categories. You can relax that assumption. You can say, okay, what is really shared among object category is the intrinsics themselves. But you're still restricting yourself to the case of there's a single object category. So you want to move beyond by saying, okay, can we not do a single object category? Can we learn something that's beyond one object categories, right? So Elliot had this earlier work called Magic Pony, which beautifully trying to reconstruct everything I talked about before, shape and stuff, but also the articulation of the horses. There's a Magic Pony. We reconstruct horses by putting strong inductive biases. You have a generative model. You can reconstruct the geometry, but also the articulation of the horses. So we thought, okay, we can move on and saying we don't only do horses. We want to go beyond a single object category. What if we do 100 different object categories, right? So that's what we're trying to do. We can extend our system to work on not only a single object category of horses, but this thing called learning the 3D fauna of the web. Now we try to make the system one single system, one model. We try to take any picture of a quadruped. Still limitations. We're not doing fish. We're not doing like birds and stuff yet. But any picture of a quadruped that you can try to learn the 3D form of the web doing testing. Again, from a single image, you'll be able to do that. Okay. So I would say the biggest change we make, still conceptually they're all kind of similar, right? Of course, if you have to implement it, that's different. The specific change we have to make is now, okay, you need to have like a semantic base of shape bank. So you have a learned memory bank of possible different base shapes. They're all quadrupeds, but you can see that they more or less also resemble slightly different quadrupeds. And on top of that, you have to do now, you have specific instance level predictions, right? So you can do the same, albedo, geometry, and lighting viewpoint as we did before. We have this articulation prediction framework, which we just took directly from Magic Pony, which is another, I said, earlier work that Elliot did. If you haven't read it, I think that's great. But you also want to predict the instance level, deformations about how these bases can be integrated and merged, as well as instance specific deformations, so that you can use that, put all these things together to explain the final object shape, articulation, and deformation given the test image. Okay. So during training, you have a bunch of reconstruction loss, as we said before. But reconstruction loss is not just like we have L2, right? No, that's part of it. But you also need to have image level similarity loss, which can be learned as well, like perceptual loss, as well as these feature matching loss, like now Dino BQ and stuff like that is really, really powerful. So we probably want to also have the matching of the feature level as well. So you use a combination of these loss, but they're all like reconstruction loss in the sense that they require very minimal supervision. The only supervision if you need if at all, is maybe you want to have a silhouette, you want to have a mask, but that is, any off-the-shelf mask, we can do it now. So it's basically learn without supervision in a self-supervised way on a collection of data, which is images of, quadrupeds from 100 different object categories. And it's category agnostic training, and you're having a pile of these images of quadrupeds. You're not assuming you have category labels. I'm not saying, okay, train a model on horses and now train a model on sheep or whatever. I just then combine a model, train one model on 2 object categories, but they're all labeled. That's not the case. Okay? We have a collection of images, but I don't have any category labels. I'm not assuming any template shapes and stuff like that. And you have these generative models inside the system. You can use it for computer vision, right? So going from a single image, turning into 3D, you put textures on it, shape on it, you can see it from different views. Because you have the articulation, you can also manually try to animate, rig these parts so you can see how these parts can be moved. The motion here did not learn. Okay, the thing is static. So we just animate them to show that you can move them because we have learned articulation. Okay. So Area Design Conference, and the work is CEPR 2024. So you're welcome to see our poster. And I would say beyond animals, beyond animate objects, there are also inanimate objects, which probably have more form that you care about, right? If you look at man-made objects, like, all these chairs and tables and furniture or buildings and scenes, right? You realize, there's actually much more regularity in these objects. This is in part because, humans have this preference about making things to be regular, right? Look at all these like wooden blocks and whatever lights, they're just like elegantly repeating themselves because human has some preference about beauty and regularity. And it's much more, obvious in man-made objects than in animate objects. So naturally, we also thought about how our system, the fact that you have these generative models can be used to explain these things. We had this earlier work about, okay, you want to go from an object, you can try to infer a program that's sort of trying to explain the shape. Just like you don't have annotations on 3D objects and physics, how can you have annotations on programs? You don't have any annotations. So you have to do it in a self-supervised way, in the sense that you have a neural network that has to generate a program. You have another neural network that has to explain and execute a program, right? So this allows you to do the program learning in a more self-supervised way as well. And when we did it in 2019, we are making the same set of assumption, that is, okay, the primitives of the programs are just cylinders and cuboids, right? Just like we're assuming things are rotational symmetric or reflection symmetric. That's not the case in real world. Of course, we want to relax it. So in a follow-up in Europe 2022, we relax that assumption, and now we're seeing entry-level primitives are no longer assumed to be cuboids and cylinders, but they are learned implicit functions. So you have learned local implicit function to capture the specific details of the object parts, but then you have this high-level program that sort of tells you, okay, these are the things that should be repeated, right? So basically, if you look at airplane, and you're saying, okay, I want this local implicit function to capture specific geometry of the airplane wing, but I have this program that tells you, okay, they have to be the same wing. They have to have exactly the same shape because I'm reusing the same learning implicit functions. And the only thing that has been changed is the action sticks, is the pose of the part, right? And that's the case for scenes as well, right? So if you look at this building and say, how can I make it taller? Right, so ideal thing I want to do, and the simplest thing I can imagine is I have a bounding box and I do interactive segmentation, I get objects, and then I say, is it possible for us to see one drag, one step of interaction, I'll just make the building taller and make the building wider, right? So this is something we did, a demo we did a few years ago, where we put our algorithm inside this Adobe Photoshop GUI. So the algorithm here, this one is actually our algorithm. But this is not an easy problem because if you want to do it with a single step of interaction, you have to have understanding of objects or scenes and multiple levels of abstraction. Right? At the lowest level, you have to understand what is the texture. At the middle level, you have to understand there's perspective geometry, there are surfaces, there are surface normals. And if you want to make the building taller, they have to face the same direction. And the highest level, you have to understand there's repetition, right? The wings and the wingles and the floor, they're repeating themselves. So, of course, we have some combination of the program structures also was learned, JDNs and stuff like that to put in the textures. So some kind of generative models will put them together into, you can think about it at a high level still, this encoder or de-render and render framework. So this is in 2020, right? I thought it's pretty cool that you can make the building taller, you stay in a corridor, you can turn it around, right? It's actually, results are very good. But the issue is, again, the world is not made of, vases, or it's not like everything is, a cuboids and cylinders, right? It's also the case that not everything is a building or a corridor, right? Nothing is perfectly repeating themselves, and there are much more wild pictures that you want to deal with. So you don't want to restrict yourself to these specific object categories. So how can we relax that? So now it's 2094, and we made this improvement at this conference. That is, we can take a single picture, arguably any picture. In practice, it doesn't work that well. So still have some assumptions, but much more diverse set of pictures, but still a single picture during testing. And then you can do null video 360 sequences. This is 0 and yes by Kyle Sargent, who is another my PhD student co-advised with Fei Fei. Okay, it's much more diverse, and quality-wise, I'm not sure if it's actually better, but it's much more diverse. You can work on any, arguably more or less any type of input images. But here we're also making a change, say a paradigm shift, we're exploring. That is, in most cases, we're thinking about generative models for computer vision. You take intelligent devices into the system, you can re-render it, right? And then you can use it to reconstruct also in different ways. So that is, I would say the structure in approach, idea one approach I presented yesterday. And here we're exploring a different paradigm, which is, I think, still very interesting. And they have the same target, but they just use generative models in a different way. That is, okay, now, what if I don't put structures inside neural network, inside the generative models, but I want to distill the structures outside, out of the generative models, right? So that's a second approach, idea two of using generative models for computer vision. That is, you take these very, very powerful pre-trained models, because now you can train generative models much more powerfully and on much larger data sets, and they work much better. So if you can take these models here, let's say a powerful diffusion model, then how much can you distill the structures outside this diffusion model, right? There's a reason that you may want to explore this change, because as we said, I'm going to wrap up very soon, in 1 or 2 minutes. Yeah, is when you go back to paradigm one, then realize there is this re-render pipeline, which is, think about it as a renderer, or it can be a neural network, it can be a graphics engine, it can be some kind of whatever, right? It can be the decoder of autoencoder, anything, right? But they're making different assumptions about the scenes, especially if you use a more traditional graphics engine, or even a differentiable graphics engine, or a neural renderer, right? For example, you can think about it as if in the middle is radiance and space, then this is like NeRF. And in the case of NeRF, then you have this re-render pipeline, which you use volume rendering. Volume rendering is great, right? It's pretty general. And that's why NeRF can work on a wide range of scenes. But volume rendering is not perfect. But any renderer is making approximations of real world. That's why they're working better on some domains and they work less well on some other domains, right? And so if the domains is what you care about, that's great. Or the renderer can be very, very powerful and they can differential, they can do everything. But to let them do that, they may be very slow. They take an hour to make a single step. But if you want to put them into the training pipeline, you want every 3 forward pass to be less than 100 milliseconds. Right? That's just not possible. So you have a lot of constraints on these renderers that either you only work well on specific domains, or just some too slow or stuff like that. Right. So if you relax that assumption, then you can think about these powerful diffusion models as a very general render in the sense that they can do pretty well and they're pretty fast on a bunch of other things. Or even if they're not fast enough, you don't care about it as much because now you're just doing testing, doing fine-tuning, doing distillation. Right. So you can just try to distill as much structure as possible from these diffusion models. So that's the second paradigm I see called this structure out approach. And so this is your MVS, more results. Single image, more diverse scenes, and you can still, doing testing, single image, you can do synoptic analysis. And finally, I'm going to wrap it up by saying, Kov and Yu, who was another of my PhD student, thought about how is it possible for us to not only just distill from a diffusion model, but there are other type of foundation models, right? Can we also distill from the vision language models or large language models? Right. So he did this work on Wonder Journey, which allows you to go from a single image or some language to not only get a 360 view of one scene, but much longer journey. Right. So a few steps. You first take a large language model, generate a long description of scene descriptions. And you have a text-driven point cloud generation pipeline to synthesize these 3D scenes, using diffusion models for text-based outpainting and stuff like that. And finally, you also use a vision language model to not only do generation, but to check its generation to see, okay, if the generation is consistent with what I want, am I just putting everything to a frame and stuff like that, right? So, you use multiple different foundation models in different ways, try to distill as much structure as possible from them. And here are some results, right? So again, similarly, you can go from a single image, and this is really like more relaxed, right? Because now you no longer function on real estate take care of it. It's much more relaxed. So you can take any picture, arguably, I think now it's really almost any pictures. And you can go, that's why we say from anywhere, you can go from anywhere to generate these pictures. And for a single picture you take, because you're distilling structures out of it, you have to capture a possible distribution, a probabilistic distribution of what a scene will be like. You can have multiple different samples from it. You can go from same place to different places, right? So it's going by to everywhere. Okay, I have to skip some slide. And this is what we talk about forms, but I have to talk more about them offline. And for motions, I'm not going to talk about them because I just don't have good enough results. So wait and save it for next time until we have a better result. Okay, so to summarize, I think there's always a fundamental question about what you learn and what you model. There's a problem in generative model, that's part of computer vision. How much do you want the end-to-end? If you want to have something inside, what is inside, and stuff like that. And also, what would be the target for generation? What would be the target for computer vision? Right. So, I think questions we're exploring and asking here is what are the minimal assumptions, right? For 3D perception, for 3D generation as well. I should put perception and generation. Right. So what's the main assumption you need for perception generation? What are the interfaces you need that you want to build a generative model? And how they can have synergy with the perception model, with the reconstruction model, because they may just be the same thing, the same set of assumptions, right? So how can they serve at the same time, both generation and perception? What are the relations between them? And a lot of things we have been doing, I can summarize them as you do inverse rendering or vision, but based on this causal, physical, and universal object intrinsics or C intrinsic, in the sense that because they're causal, they're physical, naturally you have this generative model, right? So kind of you get a generative model for free, or that's but naturally have it, and allows you to really, because you're using this causal process in the wild, explain in the wild data, you have very effective use of this in the wild. You have very effective use of in the wild data. Allows you to potentially leverage synthetic data as well. And an important part of it is the inductive biases or assumptions. Often they naturally align with interpretability and also the controllability, right? Because, why is it so hard to control a video generation model? How can we control the camera parameters? If you can disentangle the camera parameters, you get video control you can control these video generation models for free, because now you can just directly change the camera parameters. And finally, allows you to hopefully better generalize as well, because that gives you the compositionality, and compositional generalization is a very important problem that people care about. Yeah, thank you.
Okay, we have 2 minutes for questions. So maybe one or two. Yeah, please.
I think it may. I think there are two challenges. One is sometimes these equations are too complex and they're not differentiable. So if it's not differentiable, you can't really. I think I care actually quite. You're like, oh, why do you care about differentiability, right? Because you can do end-to-end optimization. Gradient descent has a lot of problems, but still best tools we have allows you to use really in the wild data. So if the equations are not differentiable, or they can be made differentiable, but they're really slow, so that's kind of a problem, right? And I think the second challenge could be, I think a lot of these, as I said, I sort of suggested is, if things are in domain, it's all good. The reason there's paradigm two is, sometimes we just work on things that are out of domain, right? If these are things that are not explainable by our generative models, usually that's a disaster. So, diffusion models and distill things out of it has this benefit of they're arguably, more in the wild. The quality, I'm not exactly sure, but they're more in the wild because you're no longer with the assumptions that come with the generators. So the issue we've been doing with all these physics-based methods or PM, there's all this entire community on physics informed neural networks, right? But the issue is, because we actually, unfortunately, we don't understand physics that well, right? So the physics equations, especially in fluid simulation, they're all just approximations. So when we try to apply them to raw data, you feel like the real world data is actually out of domain because the equations you have are so bad that I can't explain them that well. So that's another challenge.
Okay, then we are on time. Thanks, Yajin, again.
Thank you. Thank you so much.
Yeah, that works. Great.
Okay, so we are going to continue on time, actually. That's fantastic. With Katerina Frakiataki, associate professor at CNU, very well known for her work on 3D understanding from 2D video streams, awarded with all Young Investigator and Early Career Awards and an NSF Career Award. We are very happy to have you here. Thanks a lot.
Yes, thank you very much for organizing. Thank you for inviting me. Yeah, so the topic of this workshop is very close to my heart, as I'm going to explain in a little bit. So we have discriminative perception that learns the bottom-up mapping from image to labels that we care about, directly maps models the probability of y given x. Unfortunately, it also learns shortcuts to get the y from image pixels. Then we have generative perception that this top-down mapping probability of x given y, a much harder task that has seen an explosion in recent years, which is extremely exciting. And of course, the natural question that the workshop asks is, can we combine the two? So some questions that were raised this morning from Signing and Alan was about, is important, the visual quality of the generated image, how much it affects the quality of the analysis when we do analysis by synthesis. So here are some slides from 2019, actually, that remind of some talks I had given back then, that again relates to the questions about what should be the output of 3D perception. So back then in 2019, everybody that was doing 3D vision was trying to go from images and pixels to 3D shapes and then illuminance and then this type of quantities that are both impossible to get, impossible to supervise, impossible to generalize across categories and so on. You have a piece of paper, you have the book, etc. It's just impossible to go beyond vases and so on, as also Jiajun mentioned. And I'm extremely impressed by the Fauna work that was able to hold in that framework such a wide variety of, let's say, animals, which is really great. And I very much believe on the progress in that direction. But back then we really gave up. And we said, what if the output of 3D perception is not these explicit quantities, but rather some implicit representation? There are just some feature vectors arranged in a 3D grid, okay? And the only thing that, the inductive bias we're going to put is about the 3D nature of that grid. So we're going to go from 2D perspective images to these 3D feature grids. We'll be updating the grid as frames goes by, okay? So you update your 3D feature volume, and you train that network to imagine other viewpoints, much like novel view synthesis, essentially. All right, and there's no diffusion here, and everything is deterministic. And there's not even a transformer; it's just 3D convolutions, which is a terrible idea when you go from partial 3D volumes to complete volumes. But even that, we were very excited to show that, look, in comparison to other architectures that don't go through explicit 3D bottlenecks, this can generalize from when you train from 2 objects to 4 objects, while other architectures were stuck to 2 objects, for example. Okay, and again, when instead of generating pixel values, you generate contrastive features, much like what Alan was discussing. Okay, so you render feature maps, 2D feature maps from that 3D feature volume as the camera moves around. The quality of perception improves. So what you have right now is this 3D feature volume, and you can do with it whatever you do with the 2D feature maps. You can put the object detection and object segmentation and so on. And indeed, if you train for contrastive prediction, the curve is going to be higher than if you train for pixel generation back then. But I would say this has been adopted to autonomous vehicles. They get perspective images, featurize them, and geometrically compose them into the bird's eye view map or a 3D feature map from where objects are detected and so on. So you don't use 3D to directly through analysis by synthesis to make the pose of objects and so on, which is the right thing to do. Rather, you just generate a feature map that is ego stabilized, and then you put your perception routines on top of that 3D feature map. Okay, so and we are very excited that what Tesla calls the vector spaces is very much something closer to this. So this talk, I mean, also trying to think of how can we use generative models for better perception, which makes a lot of sense. I want to discuss 2 things. First, some auto-encoding models, okay, that encode and decode. The encoding is essentially perception, and the decoding is essentially generation. And I will give 2 instantiations of those models. And the benefit of those models that is a test time, because they generate the input, you can do test time training through that unsupervised reconstruction loss. And the second part is, again, how using this type of autoencoding, how can we go from monocular videos to 4D, essentially tracking in 3D across occlusions and across viewpoints. So here is how feed-forward inference, what feed-forward inference does. And I'm going to talk about point clouds right now, and I'm going to go back to images in a second. So the 3D point cloud comes in, and you have your favorite detection transformer that spits out, 3D segments. All right, we have query vectors attend to the input pixel features, and they spit out the shapes. And you can train it on your training set, and then you go out of distribution, and you ask your detection transformer to segment those shapes that for all of us, we see the familiar primitive shapes of horizontal and vertical, lines and cylinders and so on. And guess what? It fails miserably to segment those. Okay, and indeed, I trained on chairs. Why would it work here? It's extremely out of distribution. Now, if you have kids, then everybody knows that Mo Willems, author, and you are extremely surprised with the difficulty of the pictures on toddlers' books. So the toddlers do handle compositionality quite well, many mouths, many eyes, etc. And one, of course, hypothesis is, guess what? Our detectors that feed forward in nature, cortex has a lot of top-down feedback. What if this compositionality has to do with our ability to render and complete things? So here is one architecture that we're trying to explore to make this compositionality emerge in 3D vision. So we said that first we're going to learn the distribution of individual primitive shapes in terms of latent vectors through autoencoding. And then at test time, after I do that, I'm going to instantiate an architecture with multiple such slot vectors. And then I will do test time, let's say autoencoding. So I will optimize for reconstruction. And this optimization, this gradient dissection will be essentially a search over those primitive shapes so that you can assemble the new scene, okay? So this is the stage one. Essentially, you have your primitive shapes and you encode them into the slot vectors, just embedding vectors, which you then use to decode the scene. So you just optimize from this reconstruction loss on each individual shape. So these vectors now here essentially learn the distribution of the latents that can generate different primitive shapes. And what are the primitive shapes? We'll take any object category that is labeled and strip the different parts, and these are your primitives, and then feed them into our architecture. So you train your neural network with one slot vector, and then what you do is you shape multiple of those slot vectors, okay? And they all use the same slot decoder. And then you do a max pool, which doesn't have any parameters. And then you optimize through reconstruction loss, and that's it. So you've never trained on chairs or complete objects. You have only trained on individual parts. And then you start doing this essentially gradient descent. And what happens is that this operates as a search. So the network is searching over those shape primitives to assemble the complete shape. So it's searching over things that it has seen and that are familiar to it to generate the complete thing. Okay, and this search is because you both need to obey the prior, because those slot vectors are sampled from that prior, as well as you need to satisfy the rendering loss. So these are the two steps. We call it slot-centric TTA because it has slots and it has this time adaptation. So here is how this works. As time goes by during the search, the reconstruction loss goes by, so you are able to reconstruct better and better, but at the same time, you are able to segment better and better the new scene. So here are different searches, essentially. And the hypothesis here is that maybe this is what, let's say, we do when we see some unfamiliar composite concept. We try to search and figure out what are the primitive familiar things that we can assemble it with. And of course, the details matter here, and these are a specific instantiation of this. And now you can do exactly the same thing. So this is a toy example, simple to explain what's happening. You see those shapes there, they're extremely heavily occluded, but our slots have learned the individual shapes. And as we do this search, every slot recognizes and can render the complete object. Okay, so the network sees a very heavily occluded scene, but it can still decompose it into the complete shapes. So we compared our method to feed-forward detection transformers, as well as the shape program that Giacomo presented earlier. And apparently this type of test time search, okay, through gradient descent is able to do very well on decomposing complete shapes into individual primitive shapes. And it is very, you cannot do just a feed-forward inference. You need to be able to do test time, gradient descent, and this is where the red bar is higher than our yellow bar, and it's higher than other models that don't do such a auto-encoding. And also it was able to capture these extremely out of distribution shapes. The key here is that you do need to train into a set of primitive shapes in terms of cuboids. So these are like geons from a long time ago, spheres and elongated, etc. If you just train on shape chair parts, then you're not going to be able to explain those. You really need general primitives that can assemble a lot of different things. So the same thing you can do not only for point clouds, but also for images, and specifically multi-view images. You attend on the image, you render different objects, and then at this time, again, the image comes in and you are able to render it. And as you maximize, the fidelity of the image you're reconstructing, the segmentation accuracy also goes up, and you are able now to render a lot of different, you're able to render a scene from different viewpoints. So your decoder here, because it's an image, you also takes as information the camera viewpoint. And again, in these cases, you're able to do better than 2D segmenters. And of course, the most natural question is, why didn't you show this in Coco and you show it in these toy scenes? And the big problem was the decoder. So that decoder we used to go from slot back to the part or back to the object in 2D images was a deterministic decoder. And this was the major limitation of this work, as well as many other works that were using this type of autoencoding. But now we know there are high capacity renderers, diffusion models that you can probe them with any representation and generate back the image. So what if we switch to those high capacity renderers to do such autoencoding? So this is our work, diffusion test time adaptation, where we're test time adapting discriminative models, classifiers, and segmenters using generative feedback from diffusion models. So diffusion TTA works as follows. You have an image, and you pass it through your discriminative model, and you take the output of that model, which can be a classification label or segmentation map. And then the output of that model enters as conditioning to a generative model that knows how to use this condition. For example, a text-to-image condition model, in case you have a classifier on the discriminative model, or segmentation mass condition image generation in case you have a segmentor there. And then at this time, you can put here a diffusion loss, how well you can explain that image. So basically, you ask your discriminative model to infer the description of the image. So if you condition your generative model, you'll be able to get back the correct pixel. Okay? And then this diffusion loss is back propagated both to the generative model as well as to the discriminative model and are adapted at test time. Their weights are adapted at test time. And then you're able to see this nice, as you see, as we're building the generative model, is able to predict an image that looks like the right duck here, okay? So it was, or goose, whatever. So it was between Drake and goose, and as we adapted, was able to get the right answer back. And here again, from the tiger and so on. So now that we have these very, powerful renderers, we can go and test this in ImageNet and with really, really high capacity discriminative models, because the more high capacity your discriminative model, the harder it is to improve upon it with the generative losses. And you see that still we get boosts across multiple different clip backbones trained on lots of data using this combination. And then you can go in ImageNet and different here variations from the ImageNet benchmark and train your discriminative model on ImageNet and see how well it can explain the different variations. And we always get a big boost when over the basic classifier using this diffusion test time adaptation and outperform all previous test time adaptation methods that are being discussed in a neighboring workshop. Now, the biggest boost came in the online test adaptation case. In this case, data arrives and the generative model and discriminative model are continually adapted. Okay, so you see a tremendous boost in performance over the baseline classifier. And again, much higher as opposed to previous test time adaptation methods. Yeah, so this is all for the case of image classification. We also did the same thing for segmentation. And for that case, we had to use, diffusion laws that condition on the mask to generate the pixels. So basically, you improve on your inference of the mask by generating back the pixels. And I find this method interesting. Now, the details of what is the right way to do this autoencoding to really be able to use it, throw away every discriminative model and use this type of approach is still up for a debate. I do not see this type of models to have replaced discriminative models yet, but I think we are very close. And I think that the place where this is going to take over is indeed in video understanding, where you have all these occlusions that you need to understand, detailed motions of where things go. So my last part of the talk is exactly about this. So we have seen in 2013 tremendous progress on lifting 2D images to 3D models, nerves and then meshes and so on. How do we do that? Well, following Dream Fusion, you use the image, instantiate a differentiable 3D representation, and you train that differentiable 3D representation to maximize reprojection error from the view that you have, as well as diffusion losses from the views that you do not have, okay? Using a diffusion model, a view condition diffusion model, or variants of that. There are fantastic things in the literature that generate a whole video from a single view, so this has even better and more high fidelity image likelihoods for different viewpoints. So definitely this is extremely powerful and is used everywhere. We specifically have used it on scaling up simulation, environment building for robot learning and so on. But the natural question is, how much can these foundational models tell us about video fine-grained perception, tracking, fine-grained tracking, extension of objects behind occlusions, and so on? So the question we ask is, can we use existing discriminative and generative foundation models like segment anything and this view condition image diffusion to do video perception in the sense of lifting 2D videos into 4D, 3D plus time, okay, by tracking through every pixel in 3D. And this is our method DreamScene 4D, which came up a month ago on Archive. And we can see things like this. You have a monocular video, which then we can essentially decompose into background and individual objects, re-render from any viewpoint, okay, completed through occlusions, but also, link the point tracks in 3D into trajectories. So you can see these trajectories from the viewpoint of the video as well from any viewpoint. So how is this done? And why this is a problem? Well, because diffusion priors, image likelihood, right now we don't have good models that can tell us for a scene what is the same scene from a different viewpoint. Or rather, these diffusion models work much worse than object-centric ones that can tell us for a particular object what is the likelihood of seeing from different views. So what we need to do is, to be able to lift whole scenes, is to segment this scene into the individual objects, as what we show here, and then track and complete the object throughout time and across viewpoints using scored distillation losses and reprojection error. And the reprojection here is both in terms of pixel value reprojection as well as motion reprojection error. And then reassemble those into the whole scene by adjusting their scales so that, reprojection error in the whole frame is actually respected. So we're taking advantage not only of the tremendous advances of generative foundational models, but also on tremendous advances of discriminative models like SAM that can segment objects in the wild when those objects are not heavily occluded. We do rely on our model to be able to understand that object under very heavy occlusions. So the deformation of each object is represented in terms of XYZ motions of the set of 3D Gaussians, which are predicted from these triplane features that are all adapted at test time for a particular video. So this is a test time optimization method. There is no training set and there's no explicit priors beyond the priors of the diffusion model. So the object motion is essentially decomposed into that slight deformation, object translation, as well as the camera and object relation, and then we put all those together to do reprojection error at the whole frame once the deformation of every object has been optimized. So the results of these methods look like this. You see different videos of multi-object scenes that are being tracked and then they're being rendered from different viewpoints. We also did this from our own captured videos and videos from Davis and so on. And of course, for us, the biggest application is understanding human-object interaction for activity, fine-grained activity recognition, and retargeting to robots. Okay, so we want our final goal is to be able to see what a human is doing, and not focus that much on what the hand is doing and so on, which there is tremendous research effort on essentially 3D reconstruction, but rather understand what happens in terms of the object, okay? Because we want the robot to generate the same change in the scene as the human did. And here you see our initial attempts to be able to both, parse what the human is doing as well as what the robot is doing, because you do need to have very accurate robot perception to be able to do fine-grained progress monitoring of the robot's activity. And you see that in comparison to methods that actually do not keep track of objects and so on, I mean, it is harder to deal with occlusions, right? I mean, occlusion is a major point. In fact, I mean, I'm very excited about methods like Tracker and PIPS, etc., because many people say nowadays that, oh, transformers can never fail. Anything you can throw enough data, you can solve. Well, guess what? The problem of tracking any pixel is not really solved. You put a little bit more occlusions to the method and things tremendously fail. It's very hard to learn all possible, modes of cross-object interaction in a feed-forward difference way. So I'm wondering, for this case of highly deforming dynamic scenes, an analysis by synthesis method will be able to do better and improve over a feed-forward approach, not canceling the feed-forward approach. If we know when the feed-forward approach fails, we can even use it as a loss, right? By rendering our 3D trajectories into 2D, you can totally put a loss if you know when contractor fails, etc., or optical flow fails. But at the same time, we know how objects are, and you can put local rigidity losses or other better data-driven motion priors over the motions that you are extracting. And we also have quantitative comparisons on the paper, both in terms of the quality of the video that we're rendering, which, to tell you the truth, is a little bit irrelevant. So you ask humans to tell you, do you like my video better than this other method? I mean, clearly they like our video better because it is not easy to do this lifting unless you put this factorization of the scene in terms of objects, but most importantly, in terms of the tracking quality. Do your 3D trajectories, when projected to 2D, are they highly accurate or not? So these are the things I wanted to discuss. I like this workshop because it poses more questions than answers, okay? Using generative models for accurate fine-grained perception, I think, is the most exciting thing to be working on. Very, very key for accurate robot learning as well. And yes, and I'm very excited to see the progress that we're going to make as a community in the next year or next semester. So thank you very much.
Thank you, Katarina, for this great talk. So any questions from the audience? I mean, I could start maybe with one or two. You started with like feature level representations, but then in your talk, you kind of transitioned into like image level rendering. So, and this is probably because diffusion models are good at image level prediction. So do you think like this feature level approach is gone, or is there a way of combining it?
Yeah, I think you're asking whether we should be rendering features versus rendering pixel values, right? Yeah, very good question. So even in the case where we're rendering pixels, these were not rendering pixels, we're rendering the deep features of the stable diffusion that already does this autoencoding. Now the question is, do you compute those features based on image autoencoding, which is irrelevant, or you instead put some beautiful foundational DynoV2 or other features? And I think, yes, of course, the second is probably the best, or some other features of that VLMs will come up with, so you can talk in the same language as VLMs and so on. So yes, I don't believe that we need to be rendering, of course, intensities, but even in this approach, we don't render intensities. We render features that, the autoencoder of stable diffusion will translate into pixels. I think rendering features is the way to go, absolutely.
But what features then?
Very good, yes. Excellent question. Very, very good question. We haven't experimented with this. I do believe that some, video features like the things inferred from JEPA, etc., would be pretty great, where you can, or other features of discriminant approach. So when you render, you can also put your perception head, so you can interpret what you're rendering, right? So you can, what you're rendering can be still fed up to the next encoder perception module, let's say. Yes, very, very, very good question. Yeah.
Because like we had actually yesterday in another workshop, a couple of discussions on, like some people believing that video diffusion models will actually have the ultimate features because they can generate really long videos. But then we had signing, I'm not sure if you're still in the room, saying today that actually generative features do not seem to be the best features.
So yes, so I haven't read Signing's paper. I put on my download during his talk. So video, I mean, one way to see generative models, which is not what I present in my talk, is that by, generating videos, you end up learning very good image features, which you can use for something else. Okay, so that's one way, and people do this already. Everybody uses stable diffusion features for their pipeline, or they combine this with DynoV2 features. There is this beautiful papers that they show their complementarity and so on. So that's one way to go. Another way is to, use those fantastic generative models to squeeze out structure, explicit 4D structure that you can use for your direct downstream tasks, like, sub-goals for the robots, policies, and so on. This is mostly what this was about. Now, I think what you're saying is, what is this majestic perception architecture that will process videos, render back, update this latent representation, and repeat? I think this is what we're going to discuss in the next workshop, the third, I think, generative models for vision.
Yeah. More questions? Yeah, please.
So you mentioned decomposing point clouds and objects, and you mentioned geons as well. What were the properties that you defined to define those basic parts?
The basic primitives, you mean?
Yes.
Yeah, so they can be anything you want. So we experimented with two sets of primitives. The first set of primitives were directly taken from Jiajun's paper on shape programs, where he defined a set of generalized rods and spheres and different cuboids, etc. So this is one we did, and this worked very well on decomposing these weird shapes that I told you. Now, your primitive shapes can also totally be labeled parts of any object category that you have available from your annotations. And then these are going to be your essentially visual recognition primitives at test time. Yeah.
Thanks for your amazing talk. I have a little question about the Jinxing. It's a wonderful work, but does it have any failure cases or?
Yeah, it has tremendous failure cases, of course. So the most challenging part is that objects occlude one another. Okay, so what we need to do beyond the tracking the object, which we do get to some extent from this SEM, is we also need to inpaint the object, so to roughly have an idea of where the object goes. So there are two things you can do: either put very strong inpainting diffusion models, and we use the best one, an object-centric diffusion in Painter is called from the paper Gestalt from Carl Mortring's group. That was reasonable, or we adapted some video models for inpainting. Another thing you can do, I mean, the problem is that when the object moves, the visible part, you can guide it from motion rendering, but the invisible part, you don't know how to guide it. So the question is, you want to put data-driven priors of how this rest part of the object moves while you don't have actually rendering losses. These precise motion priors we don't use beyond some local rigidity losses, which are completely insufficient beyond rigid objects. And this is exactly what we're working on. We do believe that it's very easy to bake in some data-driven 3D motion priors as well in this approach.
Okay, and with this we close slightly late, 2 minutes late, but that's fine. Let's one more round of applause.
Thank you.
So we are going to meet in half an hour.
for video. Oh yeah, you can turn on there. Yeah, of course.
The full program.
Full program, yes. They don't see. Oh wait, this is gone. It's wrong. What's happening here? I lost control. There you go. Control
They're
deploy.
not AI.
Yes. Saying whatever he wants.
What a fundamental title.
Yeah. No, but this is a subtitle.
Ah, yeah.
Okay. Which I did that because it was too fundamental. Yes. That's exactly right. And we can even use a clicker here. Perhaps. I don't know what it's useful, but
So a couple of minutes, right? Yeah, it's 4 or 5 minutes. Yes, you can actually hear that's a flash.
that's such a wonderful organization.
What do you think about video diffusion models? What will you bring to the table?
Video diffusion models.
Oh, no, one question. I wanted to ask you already at the end. It's not too bad, but how do you, in one talk, actually say that there will be like a new CO3 leadership?
Yes. Yeah. So hopefully, yeah. So you should ask, do you know David Lamontney?
Yes.
Okay, so he's you co-leader this, right? That's what he said. Yeah. So he's the one doing it. So you should ask him when it's gonna come out. I'm not involved.
Okay.
So it's gonna be like the same talk as you had already today.
Which one? I had give 2 talks.
3D generation.
I had a talk on 3D generation on Monday. That would be the same talk, but
What did you do the one with today?
there was some overlap, about 100%. Say. I hope.
So there are plans, at least.
Yeah, no. I mean, it's the data's being collected. They have tons of videos. I think it's just a matter of packaging it and releasing it eventually.
Okay.
Hopefully.
Maybe even this year.
I really hope so. No, I mean, but ask David, and if he thinks that there is demand, maybe it's going to be more incentivized to actually do it.
Okay.
So yeah, make sure that to ask him.
Okay.
I think it's going to appreciate that a lot.
Nice.
Yeah.
We're actually waiting, learning for it.
Burning.
Drop him an email.
Yeah, do that. You do that. Yes, thank you. But yeah, I think the other issue is how you're going to publish that. It's just an extension of what came before, and so you need to find an excuse to publish it, I suppose. Meaning, like, how to write a paper about it.
It's bigger.
Yeah, I guess.
I guess so.
Same but bigger.
Yeah, I mean,
Award quality.
I mean, sometimes that counts.
It's not exactly the same either, right? It's just the criteria for collections, I think they've changed a little bit. It's the same nature of the data, but not just the same, I guess. I don't think. The definition of categories. It's much more open-ended, I think.
I think that how you said it's like multi-view cameras and then people can do video or something like this.
Oh, that data set. No, okay,
That's a different one.
this is a different. That's we have at least one such data set. Yes.
Okay.
Yeah, that's already available. So yeah. Yeah, no, I mean just look it up. It's
I'll find.
Yeah. So no, that one is certainly with people acting. Yeah.
Okay. So
There are 40 videos or so which are pretty long. So more data that you can possibly use. I would even download.
Oh no.
Yeah, there's a lot of cameras.
Here's the data set that you barely can download.
Yeah. We're switching to well, anyway, I think it's time. I guess so.
Okay, then we'll come to the final part of today. Kicking off with Andrea Vidaldi, who is the professor in Oxford, co-leading the VGG group, as I guess all of us know. Philip Gabler's paper awards, and we are like super happy to hear his work on 3D generative AI, new advances from his group. Thanks a lot, Andrea, for coming.
Thank you. Not this year award though. That I don't think nobody knows except who actually got it, and it's not me. All right. Right. Okay. Excellent. So thank you for inviting me. This is a pleasure to be here. So I'd like to talk to you about 3D generative AI, as the title says here. Some recent progress and advances that we have obtained both in Oxford and in Meta. So let's start by defining the problem a little bit. So what I've been talking to you about mostly is text to 3D. So that means the task is given a text like that, so a Viking axe. What you want to do is to get a 3D model of that object, okay? So it's like reconstruction, but what you have to work with is just a bit of text. There is a related problem that we're going to use, which is image to 3D, if you like. So here, instead of having a text as input, we have an image, but the goal is the same. So what you want to get out is a 3D model, which means shape and appearance, okay? Now, you look at this and you immediately realize that this is very ambiguous. So it's not just a standard reconstruction task. In fact, it's much better cast as a sampling task. So what we have here is a posterior distribution, P of M given I naught. So M is, again, our 3D model. I naught is the image or text or prompt, maybe, that we have. And what we want to really do is to draw a sample from that conditional distribution. So it's a stochastic problem. It's not a deterministic problem. So if you want to solve a task like that, probably your standard solution these days would be to use the noise and diffusion model. So just as a very quick recap, so how do you train a model like that? For images, what you have is an image, which is, say, part of your training set. You're going to add noise to that. So you're going to get an image which has less information, or information has been somehow canceled, deleted or corrupted by the noise. And then what you do is you train a network, a generator network that tries to come up with the missing information back, all right? And of course, that is usually conditioned on the additional information you have, for example, your text or prompt or your image, okay? Now, what is good about this is that these models can train from a very large collection of fairly unstructured data, right? So you can go there on the internet and you can download tons of images, maybe 1 billion of them, capture them semi-automatically, automatically using another transformer network. And then off you go, and you can train a model like that does generation very, very well. So say, for example, the Lee or Emu, if you're in Meta, all right? Now, this is great. And in theory, you could just do the same for 3D, except that, well, you do not really have equivalent quantities of 3D data to learn from. So now you're stuck. Right? So you have models that in theory could learn from that, but you don't have enough 3D data to learn them properly. So what are you going to do? So what we do normally is to try to co-opt a pre-trained image generator model, okay? So we take a model like Emu or DALI or Imagen, one of those, that has been trained to generate images starting from text. And what we do is we engineer the architecture and we do some fine-tuning using a small amount of 3D data to solve the different tasks. For example, new view synthesis. So here the conditioning is not a text or a prompt anymore, but it's an image I naught, as well as a camera C. And condition on that, you want to generate a new view of your object. Still ambiguous task, so the problem is still to sample a distribution, but we are going from conditioning on text to conditioning on an image and the camera, right? Now, why is this useful for our task? Because once you have that, what you can do is you can take your image, you can use your new view synthesizer to generate new views of your object. And when you have enough of them, assuming that these are good and consistent, then you can simply reconstruct the object and you solve the problem. Now you have sampled one version of that object in 3D. And this is great. And we're going to look at this two stages approach quite a bit today. So again, the two stages are, first, we take our prompt and we generate several views of the object. And then given those, we have a reconstruction process or maybe a network that gives us the 3D object. Okay, so that's what we're going to do. Now, the first thing you might wonder is how difficult it is to do this. So the trade-off here is how much effort you're going to put on building your multi-view generator and how easy it is to get the 3D object out to the views you get, right?
So ideally, what you really want to do is to sample several views of your object I1 to IN, condition on the image you have, I0, maybe text prompt. But what you actually can do is to sample somewhere from a distribution which is somewhere in between this one, which is the target one, the joint one, to just a product of marginals, okay? So you would like to sample from the top one, but because of limitations in your generator, actually you end up sampling with distribution, which is just some sort of approximation to that. And if you think about it, the worse the distribution you're sampling from, the least consistent are going to be those views in 3D. And so the harder it is to get a 3D reconstruction from them, right? So now we have these views which are not perfect, and the least perfect they are, the more difficult it's going to be to do the 3D reconstruction. And to try to reconcile this inconsistency, you can do different things. You can, for example, use score distillation sampling to try to achieve multi-view consistency through iteration. Or you can give that up and just have a very robust reconstruction network that can compensate for the defects in the images you give it as input. And we can put this into the sort of conceptual graph in which on one axis, okay, this is gone again. On one axis, we have multi-view consistency. So the more to the right, the more consistent the views. And then the y-axis here is the reconstruction effort. And really what you would like to be here, but you know, if you have a model that is not view conditioned at all, like just image generator model, then with condition sampling, you can still get good 3D objects out, but it's actually quite expensive and quite tricky. You can condition on one view, so that's real fusion, which is just a direct successor of Diffusion, in which you at least condition on one view of your object and you get another. That's a bit better. You can condition also on a camera, so you have 3D, 0, 1, 2, 3. MVDream, which you sample several, maybe 4 such views together. And the more you do that, the more you go to the right here. So the more view consistency are your views, and the easier it is to reconstruct the object. And in the past year, the community has developed some best practices on how to do this. So you start from a denoising diffusion model here, which is usually UNet. You have several such streams in parallel because you want to sample several views together jointly, right? And so what you're going to do is you're going to condition your generation on the input image here, and you're going to inject that as additional channel into your input, as well as through cross-attention in the different layers of the UNet. So that's one best practice. Another one is to have cross-attention layers that allow these two streams to communicate, so you can get views that are more consistent to one another. That makes sense. Free 3D. So this conference is a poster session as opposed to the Friday AM. So if you're interested, we have found a few more. So if you want to condition on viewpoint, here the best representation you can use for the camera is actually to use plaque array modulation. You can see more details at the poster, but basically that means that you encode the camera viewpoint as a bundle of rays, if you like. And this is a theme that, if you look at several recent papers, is more and more common. So that's a very good camera representation. And the other thing is, if you want to get views which are more consistent, one simple trick is to just share the same diffusion noise between all the views. And because these networks, they tend to be continuous, they are continuous functions, then you're going to get views which are more similar and more consistent automatically. And so here you can see some results from free 3D. So these are 3D-like generations where there's no 3D model underneath. It's just simple these networks that is able to generate these different views. And okay, it looks fine, but you know, there's more to come. All right, so this is free 3D, so it's maybe a bit more consistent, so a bit easier to do reconstruction from it. But if you want to go even further, one thing you can do is to switch to using, as a starting point, not an image generator, but a video generator. So in Meta in particular, we have EMU video, and they feature even better models. But the point is that because these models, they're shown on videos, they already have some level of understanding of 3D geometry. And I think this is also very clear in models like Sora, right? So once you have those, it's intuitive that you could take those as a starting point and then fine-tune them to generate new views, and you should get more and better, more detailed, better consistent views. And this is actually what happens. So you see here the input image. On the right, you see the little video that's been generated by putting that into this video generator, which was fine-tuned for the purpose of generating new views. Okay, so that's what we have here. And because these videos that you generate are fairly consistent, then you don't need to struggle too much to reconstruct a 3D object from them. You don't need to use coordinate distillation sampling. You can use something as simple as 3D Gaussian splatting, if you want to call that simple. Everybody knows about that. Just as a quick refresher, 3D Gaussian splatting is just a representation of the world that is a collection of 3D colored Gaussians with an opacity. You can think of those as 3-dimensional pixels. Of course, this is very large because if you want to see them even from back there, but really it would be a very large collection, maybe 1 million such Gaussians, really tiny, that are kind of conceptually equivalent of 3D pixels, really. Once you have a model like this that renders really fast and in differentiable manner, so it's actually quite easy to fit it to data. So you have an image like that, and in fact, you're going to have several views of your scene. You have a rendering function, a rend, that takes as input the Gaussian mixture, the cameras, gives you the pixels back very, very quickly and also very efficiently in a differentiable manner. So now you can try to optimize, minimize the reconstruction loss with respect to the Gaussian model you have, and the good things should happen. In particular, you should be able to reconstruct your scene in terms of these three-dimensional Gaussians. So this, if you apply that to the output of our fine-tuned NEMO model, that's what you get. So the idea is that these two should be very, very similar. One is a video, the other one is the actual rendering of three-dimensional model you've got from that video. And if you carefully, you see that this is a little bit more blurry because the input views are still not completely perfectly consistent, but it's still pretty good. And the key advantage here is that this is way faster than using the STS loss. So this takes just a couple of minutes for each object. The STS loss could take, say, 30 minutes, so maybe even more, maybe an hour, okay? So, and this is because we have put more effort in generating more consistent views to start with. So it pays off to do that. Now, the other thing you can do is to get better 3D reconstructors. You can use Gaussian splatting, which is fine, but there is no intelligence in that in a certain sense because it's just pure optimization. But on the other hand, you can use machine learning to try to do reconstruction faster and better in the sense of being more robust. So here, a lot of progress has happened in the community. A typical example would be large reconstruction model by the folks in Adobe. Excellent progress there. So this was also very inspiring for our work in Meta and in Oxford. So what you do there, you have a big transformer that takes as input either a single image or a small number of views and spits out a representation of the object that would be volumetric, using basically a NeRF, all right? Great, works very well. The problem with that is that it takes more than 380 GPU days to train the model, okay? So it's a large model, it's in the name, right? It takes a long time to train it. Works well, but if you're in university, you look at this and you cry, okay? Because I have a job at Meta, but also in university, half of me was actually crying when I saw that. So we wanted to develop something much, much more efficient. And this is what one of our students in Oxford came up with. Again, an approach that really struck me as very strange initially, so I didn't believe in it. The student fortunately did, and he made it work, which was really amazing to me, okay? So what is the idea here? So this is called the splatter image. It's like another theme, I guess. But really what this means is we do Gaussian splatting at the level of individual pixels. So that's why there is an image there. And we convert each pixel to a 3D Gaussian. So the way we do that is by simply designing a unit that again operates on an image as input and produces as output another image, which has the same resolution, but now the pixels are not pixels anymore. These are the parameters of 3D Gaussians, okay? So what this means is, again, we have an image, a bunch of pixels, a camera center. And for each pixel there, we come up with the network comes up with a bunch of parameters, sigma, mu, capital sigma, RGB plus, and delta. These are the opacity of the Gaussian, the 3D location of the Gaussian along the ray, the shape of the Gaussian, the color of the Gaussian. It could be just RGB or maybe spherical harmonics if you want directional color, and then delta, which is an off-ray displacement. Okay, and that's really, really crucial. So what does that mean? So, okay, here we have the three-dimensional center of the Gaussian, which is along the ray that goes through that pixel. Fine, everybody understands that. Just you can do that using depth estimation. But in addition to that, we have a delta vector that moves the Gaussian off the ray. Okay, potentially. It doesn't have to, but it can. And of course, we have one of those reconstruction or Gaussians for each pixel. It's also possible for the model to set the opacity to 0. So if the model decides the Gaussian is not useful, it can shut it off, right? And so how well does this work? Quite well. So this is applied on one category in Code3D, which is a data set of multi-view images of different kind of objects, in this case, teddy bears. And to the left here, you see the input image, and to the right, you see the spinning reconstruction where the camera is moving around the object, okay? And something should strike you as surprising. This definitely surprised me. So you get the reconstruction of the background. It is blurry because this is regression, it's not sampling, right? So you're going to get slightly blurry results, but you get a bug. So that's possible. Again, this is pixel oriented, so this shouldn't work. Also works for something which goes beyond single category. So this is trained on observers and then tested on Google scanned object, and it still works quite well. Now going back to this problem of why does this work? Well, here you can see why, or how anyway. So you have an input image, like either a car or a chair, And then you see here, these are the opacity channel. So everything which is black has been switched off. Everything which is not black is a Gaussian, which actually exists in the reconstruction here. And you can see that you get something which matches the pixels in the car, but then you also get a bit of information beyond the car boundaries. And this is where the Gaussians that actually model the back of the object actually live, all right? So you see here, for example, that we have this little circle. This is this wheel at the back, all right? So this network is smart enough to be able to say, okay, this is a pixel which is off the object, so I can use it to try to model the back. And it does that automatically, which is really nice, because the advantage is that you still have to work only with the image-to-image networks, which is very simple and very efficient. And efficiency here really is the key. So here you see performance against the GPU days in training. This is the new synthesis quality. And the message of this graph is, it works well for reconstruction, comparable to state-of-the-art, but in terms of training, it's much faster. So this takes 7 GPU days. It doesn't take 300 GPU days. It means that if you're in university now, you're happy because you can actually play this game and still get relatively competitive results. So in fact, very competitive results, much faster though, okay? And it's also much faster test time. And of course, once you render it, it's so super fast because this is just Gaussian splatting. Recently, we have moved beyond object into scenes. So you can apply the same concepts to reconstruct the entire scene. In this case, you wouldn't have, reservoir pixels to use because everything is occupied here, but you can simply sample 2 Gaussians per pixel. And there are tricks you can, look up in the paper to make sense of that. And you can get a nice 3D reconstruction as well. And the good thing here is that this generalizes also very well. So we train it on a real estate 10K because it starts from a very powerful monocular depth estimator network that we fine-tuned to add these capabilities of producing discussions on the fly. Then it turns out that training on real estate generalizes to outer domain in Kitty, and you're still going to get high, in fact, in this case, state-of-the-art new synthesis results, at least for this kind of benchmark. Okay. And again, this is great if you're in university because this takes only a couple of GPU days to train. You don't need gigantic GPUs either. Okay, so that's part 1. Part 2, I would like to move on to another thing I want to discuss with you today, which is Meta 3D Gen. Okay, so this is about the result about a year of work that we have, our team in Meta has done on the task of text 3D. And this conference, we're presenting the first results the group has obtained. So when we set out to solve this problem, our goal was really to ask ourselves, what do we need in terms of quality to satisfy professional users? So that would be people that, say, develop video games for a living, or maybe you want to use that in special effects, or maybe in the metaverse, right? So we want quality which is sufficient enough so that you can actually use it in real applications of 3D computer graphics. And so there are many requirements that you need to satisfy. So that's why 3D generation is, in my opinion, a lot harder than generating just images or movies, all right? Not to say that that is easy, but when it comes to the generation, you need to think about quality of the shape, quality of the texture. That's similar to image generation, video generation. You want to have also high quality control or high fidelity or high control. Fine, that's also common. But then you also want to have materials, you want to have parts, nice UV topology and quality, nice mesh topology, rigging, animation, blah, blah, blah. All these things that go beyond what you do normally when you generate images and videos. So it's hard. Today, we're going to focus on these 4 things, and we're going to start discussing materials. So materials means that it's not enough to estimate RGB colors for your object. What you want to estimate are material properties. You want to estimate a bidirectional reflectance distribution function, or BRDF for short, because this is what you need in computer graphics to be able to relight your object, put it into a new environment to make sense with the light source you get there, right? So what you want to estimate is the albedo, intrinsic image, or base color. These are different with the same thing, although not all of them with the same level of accuracy. So this should really be called base color in our model. And then you also have roughness and metalness, which are descriptors of the material you actually do have. And so this says a pug made of metal, so you get a dog, but the metalness is really high because it's supposed to be made of metal, and so it's all shiny. And now once you have that, you can change the illumination here, so you can see different environment maps. And once they reflect off your objects, it makes sense because now the materials have been modeled, not just the color, right? And now you have control over materials because with your texture prompt, you can say something like a cat made of shiny plastic. And now you get that roughness is really low because this is shiny, so it's not rough. And the metalness is also very low because, well, this is plastic, it's not a metal, right? But then you can say shiny silver, so roughness is low, but now metalness is high. And again, you see that it makes sense when you render it with an illumination map. Thank you. And then now you can see this much better actually. Rusted iron, rock. So you get roughness high, metalness low, and then you get rusted iron. So you get high roughness as well as high metalness because this is rough metal. Yeah, it was better before, but okay, thank you. All right. So how do we do this? We need to generate this PBR channel, so metalness, roughness, and the albedo. So there are two options you can pick here. So one is to charge the multi-view generator network with generating the information you need, right? So you generate several views of your object in RGB space for the albedo, but it also generates two additional channel, roughness, metalness. This is fine. You can try to do that, but remember that we learned this multi-view generator by starting from a model that was trained to generate natural images. So the statistical gap between generating albedo and generating roughness, metalness is actually quite large. So if you try to do that, you sort of destroy the good quality of these models here. So the gap is too big, right? So you don't want that. On the other hand, this is nice because you have all the information you require to come up with a reconstruction of those quantities. So the reconstructor network here, or the reconstruction block here, would have an easy life. The alternative is, well, you don't try to force this model to generate roughness and metalness. You just generate a shaded appearance, which is very close to natural images. So that's easy for this model to do, or really easy. But then the reconstruction network has a hard time because mapping this to roughness and metalness is actually very ambiguous, non-deterministic. And if you remember, this reconstruction network is deterministic. So that's not very good for it, okay? So the solution we came up with, I'm not saying this is the only way of doing it, but that's one good way we found, is to task this network here with generating the albedo. So RGB colors for the albedo, as well as the shaded version of your object. And these two quantities, they are fairly close to natural images that are easy for the model to actually generate. And then by comparing the albedo to the shaded version of an object, then this network, the reconstructed network, which is deterministic enough, has an easy time coming up with the roughness and metalness by itself, inferring them. Again, so what does it mean? So this is what you get if you reconstruct 4 views in the shaded space, and this is what you get if you do the same in the albedo space. Again, shaded, albedo. And you can see here, for example, that in the shaded albedo version, you don't have highlights here, but in the albedo, in the shaded version, you do. And the reconstructed network looks and compares these two quantities, and it knows that that has to be shiny metal, essentially, okay? I can infer it. So again, this is what you get if you try to reconstruct your materials using secure views which are shaded. And you can see here that this is not quite correct because the metalness is everywhere, but it should only be on the bit of the bear where he's wearing his armor, right? But if you do provide these two different inputs, then you actually do get that. So you get that the bit of the clothing which are metal-like, actually they light up in the metalness map. So it gets much better. Okay, that's one idea. Here's another. So we also wanted to get better quality at reconstructing our shapes and the corresponding meshes. So the question is, which kind of representation are you going to use to do that in your reconstructor? So we don't do meshes directly, although probably that's the holy grail. So some people are starting to do that now. We still do the reconstruction in 3D space using an implicit or explicit representation like Gaussian splatting. So but here you have a choice. It's not a mesh, but you can use a volumetric representation like NERF, or you can use Gaussian splatting instead. So which one would you pick? It's a question for the audience. Okay, here's the answer. Well, it's not obvious, right? So Radiance fields, they are nice in that they give you good surfaces when you go there with, say, matching cubes to extract the mesh. And they give you very nice regularization, good global convergence. But it's a bit slower than Gaussian splatting in terms of rendering. But most importantly, when it comes to backpropagation, they are disaster in terms of memory consumption, all right? And the reason was going to be clear in the next slide. But basically, that means that you can only render a few pixels at a time before exhausting the memory of your GPU, which also means you cannot really use image level losses. So you're limited to train with PSNR, you cannot use LPIPs. Now, it's important because remember that we want to reconstruct frame images which are not completely consistent. So you want a loss for the construction for training these models, which are actually a bit forgiving. So much better to use LPIPs here. Gaussian splatting is better, it's faster, uses much less memory, which means you can render entire images very effectively, and then you can use an image level loss to train your model, okay? The downside is that you get surfaces which are not quite as nice. I know that there are works now that are tackling this problem specifically, but at the time, you couldn't really get very nice surfaces of Gaussian splatting, which is a problem because we want to have 3D meshes for our artists to use, all right? And then they are not quite as regular in terms of training. So when it comes to training robust things, well, maybe NERF still has an edge, okay? So now the problem with NERF, though, is the memory bottleneck. And why is that? Because we are shooting these rays and you're taking these samples, and each one of those things should be differentiable, and it is differentiable. But if you implement that with AutoGrad, then all these samples get instantiated in memory of your GPUs in terms of their gradients. So the space complexity is R by P, where R is the number of rays you're shooting, basically 1 per pixel, and P is the number of samples you have for each ray. And that's terrible. So you can easily use 10 gigabytes for rendering a single image, all right? You want to render several images, you want to have a large mini batch size. So yeah, bad idea. So what we did was to develop light plane kernels. So these are just an implementation of some popular versions of NERF that use basically fused kernels. And the nice thing about that is that when you do backpropagation, the space complexity is not R by P, but it's simply R. So it has the same space complexity as Gaussian splatting, okay? So we are making NERF as efficient as Gaussian splatting, maybe not in terms of speed, it's still a bit slower, but certainly in terms of memory consumption when you want to do training. And that's enough to actually be able to actually use it in practice. You see here a little graph showing the image size from 16 by 16 pixels to full HD. And that's the amount of memory which it takes to do AutoGrad backpropagation. And you can see that there is an order difference of, 3 order of magnitude difference. So it's a huge, huge, huge difference. And this is why this is feasible and these ones are not really, when it comes to training this kind of reconstruction models. At decent resolution anyway. The other thing we did was to change a little bit of representation. So we don't use just opacity, we use a sign distance function that are known to give you better shapes. So you can see that here. So this is reconstruction using opacity field, and the same using sign distance functions, much neater in terms of the details. We didn't invent that. We used the vol-SDF formulation for this. But what we did was to implement that efficiently in the light plane kernels. And that also together with some laws which are based on the ground truth shape of the object. So check this out if you're interested, but this is actually in practice quite useful. All right, now with this, now we have this reconstructor, you get your 3D shape. You can use some standard matching cube and UV mapping method like XAtlas to get a mesh with a corresponding UV map. And from that, you can go back to your 3-dimensional volume and sample the corresponding texture. Great. And this again lives in PBR space. So we have albedo, roughness, and metalness for that. Good, but this is what you actually get in terms of quality of the texture, which is fine for this particular example of a popcorn box. It's a bit messy because we use XAtlas, but most importantly, you're gonna see that the details of the texture are a bit blurred out. And the reason is that we're sampling them from this volumetric space, which is good, but it's not perfect. You can do this different thing though. So you can go back to your views. These are the output from your multi-view image generator. And you can try to resample the texture based on the UV map you get and the 3-dimensional shape of your object. Now you're going to get sharper results, but they are sparse. And the reason is that not all the pixels in your texture are visible in all the views. And so these things also are slightly inconsistent because the views in the cells are slightly inconsistent. So what we did was to develop yet one more network that takes this initial texture map, this additional back projections, and process them, choosing for each pixel in the UV space which one is the best version of it, and also fixing some mistakes, interpolating when needed, extrapolating where there are occlusions, et cetera, et cetera. And you can get out a much better texture. So let me show this zoomed in version of that. So this is before texture enhancement and then after. And you can see that the details here of the writing, for example, are much clearer. And you can see this even better here, where we have reconstruction without this texture enhancer, the extraction width. You can almost read what's written here. In fact, I think you actually can. And this is the ground truth. Another example, you see the I/B is much sharper. The details of complex geometries, they get reconstructed better as well, texture better as well. And here you can see some examples of the object we can get, okay? And because this is physically based rendering, you get your llamas with materials, and you can change the illumination, everything responds as it should. Final concept, this is good, still not good enough. So what we wanted to do was really to get very, very, very good textures. And the idea here is, okay, so we got to some points so far, but now we have a 3D object. And given a 3D object, we can use that to go back to the problem of generating a texture for it. And given the knowledge about the geometry, we can actually increase even further the sharpness, the quality of the texture. So now given the prompt and the 3D geometry, we go back to this problem of generating a texture and we get much better results as a consequence, okay? And because this texture generator now can work even for a different prompt, we also get texture editing capabilities. The way this works is actually quite simple. So it's the same story as before. We want to generate 4 views of our object, but now in addition to conditioning with text, we condition with the representation of a 3-dimensional shape in terms of position map as well as normal maps. Normal captures the details of the geometry, and position map gives you some sort of absolute reference for where the 3D points actually are. So you see that the colors, they match in the different views, which make it much easier for this multi-view generator network to actually give you texture views which are very consistent to one another. And this is really crucial. The rest is going to just be a few results, so bear with me. So here's this is not generated, this is a 3D artist rendition of a butterfly, but now you can use the texture network to apply a majestic monarch butterfly render to it. And it's not a render, sorry, it's a texture map. And it looks quite nice. And you can change that to make it also very complicated. A magical butterfly, arcane sigils on its wings, sparkling glitter on its body. I have no idea how we came up with this, but yeah, whatever. It looks very nice. And then time to put everything together and then to close. So this is Meta 3D Gen. These are the sort of results we can get now by combining this texture regenerator with the text 3D method that we just discussed. And let's make the spin so you can see how the object looks like from different viewpoints. I think the answer is, in my view, quite nice. Because we have a texture generator, we can apply different styles, but without changing the shape of the object. So we have here a style, Christmas style, and we let it spin. And soon enough, we should change, say, into a horror style, which is possibly quite the opposite. Okay, and it looks fun. And again, this is all quite fast. Gonna more of that in a second. We run some user studies comparing to at least some dominant industrial competitors like Rodin, Mesh, and Luma, and we win out, especially when it comes to quality for complex textual prompts. And you can do a breakdown, and you can see here that the higher the better, means that our win rate is yes higher, and this increases as the complexity of the prompt increases. These are the results that Luma get with the same sort of prompts. These are results in Mesh with 3 gets, Tripo 3D. They're all quite nice, really. So now we can compare all of them. So these are all kind of state-of-the-art methods. And then we can zoom in, and I'll let you be the judge. But I think it's quite convincing that at least in these cases, we have an edge in terms of either quality, realism, or correctness of the texture. Okay. If you want to know more about this, we have 3 papers that are coming out hopefully by the end of this week. They're done. Okay. One of them is text 3D. The other one is text generation. Then there is a Meta paper from Meta that combines the two into this very nice high quality reconstructions, also generations. Okay, so time to thanks our team in Oxford, our sponsors as well, team in MetaGen, Gen AI. So these are the folks that are behind this effort. And yeah, just to conclude, what I presented to you today was some progress in generative AI. So started with some best practices, 3D, for example, in how to design these models. Control, so going up to material control here, where you want to specify details of your objects that go beyond just the shape and the appearance. Quality was also very important for practical and real-life applications. So, you need to pump this up, and you can do it, especially when you combine with very high-quality image generators in the first place. But then you really have to work hard in order also to get very high-quality text and shape generation as well. And for folks that are not in industry, efficiency, I think, is also very important. I think also for industry, to tell you the truth, but especially for academia. So we have this class of models that can do at least 3D reconstruction very efficiently. And because those are really a core component of 3D generators, then they can have an impact there as well. In fact, they did have. So there are already papers that use this sort of technology for 3D generation, text 3D too. Okay, that's that. Apologies for being slightly over time.
Okay, thank you. We have 5 minutes for questions, and let me maybe start with one. So when are we going to get the parts, rigging, and animation?
I cannot deny we're working on parts right now. Okay. For animation, I mean, there are plenty of people that are working. This is a very crowded area, so there are already plenty of work that look into that. So we already have it. In terms of our work, yeah, upcoming, I suppose. That's what you could say. Yes.
Also with like skeletons and rigging?
Eventually, yes. Now we're thinking about parts. So this is another thing which is very important for 3D artists. They don't really like to have this sort of monolithic reconstructions in which, you know, the turkey here is glued to the plate. They want to have separated components so they can animate them, maybe edit them and do stuff with them. All right. So yeah, that's not something we have done, but we'll look into it.
Do you also care about the mesh topology? Like, you know, artists, I guess, care about, you know, meshes being, you know, regular around the mouth and having.
Yeah, you're guessing all of our some internships here, but yes, pretty much. Yeah, that's very important as well. So we're thinking how to do that, and yeah, we just started basically to work on that. Again, there are other methods that might get currently better mesh topology because they actually cared about that before we could get to that. But yes, that certainly is also a very important problem. And I'm going to spin this again just because it's fun. Okay.
Yep.
Yep.
The question is, do the model has some tendency to generate symmetric objects? And if it's true, what happens?
Okay, so this is a very interesting question. So we don't do anything special for symmetry, but if you look at the back to the dinosaur here, you'll see that even the texture tends to be quite symmetric. So this is being picked up completely automatically by the model. We don't do anything special without forcing it. Okay, so when you don't have to have symmetry, like here, for example, you don't get it, but when it makes sense for the model, you do get it. So this is purely, but the behavior is entirely learned. We don't do anything special for it. Yep.
So most of the text 3D or mixed 3D models are fine-tuned using data sets like observers. So do these fine-tuned models flag the generalizability and the diversity of the underlying models?
It certainly does. So it's a tricky business. So we do have an internal data. So we don't use observers for reasons that you can imagine, but we have an internal data set which is conceptually very similar, and we use that. So pretend we are using observers. We're not, but pretend we are. So we are not using all the data we could, because if you use too much, then we destroy the ability of the model to generate nice things. So that is certainly is a problem. Okay. I don't know that we have a good solution yet, but that would be one area in which, if you're interested, that would be very helpful to us if you could solve that problem. Thank you.
I saw lots of the work that are in the object centric, but it seems the approach is also general enough to generate like full 3D scale. What do you see the gap?
Well, it's just more complicated, I suppose. So when we're dealing with a single object, it's easy because having a single mesh makes sense. You can look at it from all possible viewpoints very easily, whereas looking at the scene from all possible viewpoints is harder, et cetera, et cetera. I don't think conceptually is hugely different, but it certainly makes your technical life easier. So that's why people are focusing on that first, I think. But you are hitting on the nail in the sense that, yeah, doing objects is not enough. We want to create universes or metaverses.
Okay, I guess a very nice final word then. Thanks again.
Thank you.
So I'm muted and need to present.
Yeah,
exactly.
you're sharing. Yeah, that's good. And are you muted?
I'm not.
Yeah, that's great as well. Good. So we are actually on time. That's fantastic. So we're going to, it's a big pleasure to have our final speaker here, Federico Tombari, who is a research scientist and manager at Google, leading the research to product team in computer vision and machine learning, I think across North America, Europe, and he's going to tell us about creating 3D assets from diffusion models. I think highly related to what we've heard earlier. Very much looking forward to your talk, Federico. Thank you for being here.
Thanks. You're going to get another 40 minutes of 3D asset generation. But it's the last talk for today, so bear with me. I also want to thank the organizers for the nice invitation, for the introduction. I'm very happy to be here today and to talk a little bit about our work on generating 3D assets, specifically with diffusion. And so we've seen also, let's say, with the previous talk from Andrea, about some differences between generating 2D images and generating assets in 3D, and there's clearly like a gap in this sense, and it's really hard to fill this gap. And so with images, we can now get we have generative models that are particularly realistic in the way that they can generate results, but they can also be now used, for example, for editing. So we can specify in a pretty detailed way which area of the image we want to modify. And they tend to be very accurate in that sense. And these type of things are really hard to bring towards 3D. And so one of the things that we started looking into and asking ourselves is what is the best representation that we want to use for actually generating things in 3D. And in this case, this is a bit of a summary that I made where we can see on one hand representations that are particularly, let's say, detailed. They actually capture a lot of information about the geometry of the scene, the semantics. We can think about point clouds, 3D meshes, voxel maps, and so on. And on the other hand, we try to, let's say, abstract away. And sometimes actually using this type of abstractions of the scenes is something that also helps the generation. In particular, we're going to see that this is a nice way to condition the generation process. And so what I'm going to present to you today is actually how to do generation of 3D assets, in particular scenes and objects, across different types of these representations and powered by diffusion. So I'm going to talk in particular about 3 works that we recently published. One is text to 3D mesh. The other one is text with nerve to another nerve, and in particular is how to actually insert 3D objects in a given scene rather than generating them from scratch from a prompt. And finally, a work that looks into, actually a series of work that looks more into conditioning 3D mesh and 3D layout generation conditioned by a scene graph. So starting with the first one, so in this case, we are particularly interested in something that we've seen also before, this task of generating 3D assets from a text prompt. And we are envisioned, let's say, this type of applications. We're part of Google AR, so we are also interested in applications that, let's say, touch particularly closely this type of AR application, so we can take something out of the box that we can generate and place it in a real world scene. And so for us, it was particularly important to actually have a easy-to-use method that could generate an actually implicit representation as an output by the 3D mesh that we could directly use for this type of application. The other aspect that was very important for us and we wanted to improve on with respect to certain methods at the state of the art was actually to make the results more realistic. So we've seen, for example, Diffusion, that is a very effective way to generate 3D assets from prompts, but tends to have this type of, let's say, oversaturated and not very realistic, a little bit cartoonish kind of effect. And that's something that we wanted to improve specifically with our work. One of the, let's say, pillars of Diffusion is actually this very bright idea of square distillation sampling, where the idea is that we can actually generate and optimize basically a neural radius field, and then we can render image iteratively. And these images, then we can add noise. And then the idea is that we do some sort of noise prediction. And by predicting the noise and making the difference with the ground truth, the noise that we actually add, we can, let's say, find a way to keep fine-tuning the weights that are inside our MLP within the NERF model. And so we can practically have an iteration where the diffusion through imaging is actually done on images, but this tends to go back into the NERF model and provide very consistent results in 3D. So it's a very powerful way that leads to fantastic results with this type of characteristic that I mentioned before. And so our method text mesh is based on 4 main steps. And the first step is actually to pick what we think is a better, let's say, 3D representation for the data. And so we started from this, let's say, analysis of the differences between neural reference fields and sign distance functions. And neural reference fields, we know that they are particularly suited for novel view synthesis. So let's say they clearly excel at this type of task, but they tend to neglect the underlying geometry. So it's hard, for example, to extract 3D meshes out of that. They're not really designed for that. While sign distance function, it's kind of the other way around. So these are 3D representations that have been used for 20, probably more years, and they are used and developed specifically for having a good power for representation from the underlying geometry, but they're not designed, on the other hand, of course, to render and optimize using a set of RGB images and for novel view synthesis. And so there's now been a set of methods recently proposed in literature that try to kind of bridge the gap, right? And so they're called neural distance fields or neural occupancy fields, and they try to get the best of both worlds. So they have a 2D representation that can be suited for novel view synthesis and for rendering, while having an underlying geometry that can be very quickly and very accurately extracted. And so that was the starting point. So we developed an SDS kind of framework where we intrinsically replace the NERF with a vol SDF. Vol SDF, for those of you that are not familiar with this approach, is one of these, let's say, methods that tends to use together a volumetric representation within a neural reference field. And the rest of the approach is actually the same for this first step. So the main difference, as you can see here, is that we can already get a much better mesh out of this. We can get much better details in terms of, for example, the edges, and we get a very bounded 3D mesh that we can extract directly from the zero level set using marching cubes. And so once we have a nice 3D mesh, the next step that we want to apply is an improvement of the realism, right? As we mentioned before, let's say, problem of this cartoonish effect of the diffusion, I think it connects to what Andrea explained before, that there's this trade-off between, let's say, the realism that we're going to get to the images that we want to impress, actually we want to impress in our 3D representations. And on the other hand, the fact that we actually want to have something that's geometrically consistent and geometrically accurate. And so if you want to, let's say, have this kind of high guidance on the geometry, you're going to lose, on the other hand, in terms of realism, and vice versa. And so in this case, what we're doing is practically the idea of extracting views from canonical viewpoints, and then use that on a diffusion model to generate some pseudo ground truth images that are based on the current mesh. So what we do is actually we take this rendering from the canonical views, we apply conditional stable diffusion. In this case, the conditional stable diffusion is very important because we condition on the depth. The reason that we condition on the depth is that we don't want to change the underlying geometry, right? Because we're going to just bring this back on our mesh. And so it's really important that the geometry is unchanged. And at the same time, this improves the quality and the realism of the image. Now, there's one problem, is that if we render from canonical views and then you individually and independently feed this to your diffusion model, then you're going to get, again, inconsistency, right? For example, these are the four canonical views of this mesh, and then you can see that the diffusion process applied independently tends to, let's say, create large inconsistencies on the object. And to try to fix that, what we're doing is actually to tile images together. And by tiling, we, let's say, notice that the stable diffusion process tends to increase quite a lot the consistency of the results. And so the last step is that we bring back this texture that we have now improved in terms of quality back to our mesh. Of course, the canonical views might still miss certain parts of the mesh that are not well captured because they are, for example, occluded. And so we have a final fine-tuning step where we actually fine-tune directly the RGB texture of the mesh. So what we're practically doing is we apply a loss function. Actually, it's two terms of the loss function. And in this case, what we're going to optimize in terms of, let's say, the way that we're going to apply our gradient is directly on the values of the RGB texture of the mesh. And this, again, tends to clean up and remove the few inconsistencies that are left by, let's say, propagating these two losses. And so these are some of the results that we get from different prompts and the associated 3D mesh. Again, this is a method that gives you a 3D mesh out of the box. So we think it's particularly useful for many applications. This is a comparison that we made quantitatively, although the metrics are, let's say, we can provide a limited signal in terms of improvements. We can look more at the qualitative examples and we can see how the method compares in terms of realism and reduce cartoonish effect with respect to, for example, Diffusion and Magic 3D. And this is some additional results that we got. Good. Of course, with respect to the time when we publish this work, there's a lot more new methods out there. The field is literally exploding. These are some of the more recent results, and this is also, let's say, they provide some of them provide a very interesting way also to improve as future work the text to mesh work that they just presented. Okay, moving on with the second topic. In this case, the idea was to focus specifically not on the general purpose, let's say, generation task, but actually to do insertion. So we only insert objects, and we start from inserting objects in a neural regions field representation of a scene. Our starting point in this case is instruct nerve to nerve, which is a method that was proposed last year, and it's a text-driven 3D editing approach with 2D diffusion models. It's extremely good in providing flexibility to take a text prompt and then edit the 3D scene represented as a nerve in different ways. For example, changing the styles and changing also other characteristics of the scene. The idea of the instruct nerve to nerve method is that it does this kind of like iterative fusion of 2D edits. So the edits are done on the images, and then they are gradually fused back into 3D representation in order to avoid inconsistencies. Although we still notice that the final results are prone to 3D inconsistency of the edits. So for example, there's some, you can see that depending on the viewpoint, the results tend to change quite significantly in the type of edit that's being made. That's kind of normal because the edits are done. I think this is gone now. Can you still hear me? It's okay. So you can see that depending on the viewpoint, the edit changes quite significantly, right? And so once you start to throw this back into your 3D representation, it tends to create inconsistencies. This is one of the main issues. And the other one is the so-called localized editing issue. So whenever you, for example, specify a specific location when you want to apply the edit, say, for example, you want to create a parrot specifically on the left shoulder, then sometimes this is not very well, let's say, interpreted by the diffusion model and tends to create this type of inconsistencies. And so we wanted to improve on this by starting from a simplified assumption that we want to insert objects in the scene. And the idea is that we expect the user to provide an annotated reference view. So we have a render view from our nerve scene, and then we have the user that has simply to put a 2D bounding box as a starting point. And in addition to the 2D bounding box, of course, we expect a prompt that is the definition of the edit that we want to make. And this is how we're going to start. So the first, this is the entire pipeline. I'm going to explain it briefly step by step. The first step is to create the 2D object edit on the image. And then we're going to warp the 2D object edit into the 3D model. And finally, we're going to merge the 3D object with the scene. And so the first step is actually to start from the annotated reference view. And then we use a simple model like image and repaint, to apply the edit on this 2D view. The idea of this image and repaint is just, as I was briefly mentioning at the beginning, it's a way to edit an image based on a text prompt, right? And so we can really do like something that's very localized and to the area that's specified by our bounding box. And this kind of tends to really help in terms of the localizing painting problem that I just described before. Once we have this edited reference view, then we have to throw basically this object into 3D or lift this into 3D. And for this, we use a method called sync dreamer. It's practically a method that generates a set of multi-view images from a single image. And then from this, we can create our nerve for the object. In this case, we have our own, let's say, fine-tuned version of sync dreamer, which is trained on object-verse data set, which is around 800K 3D objects. The next step is actually, once we have the nerve of the object, now we need to put it back into the scene. And for this, we have developed a specific 3D object insertion stage. The first thing that we need to do is to actually estimate the depth. And so for this, we use a monocular depth prediction model. In this case, is Midas. And so we start from the image, the input image. We apply the rendering of the object, and then we estimate the depth. And so once we estimate the depth, then we have to do an alignment between the estimated depth with the object and the nerve depth that we get from our nerve model of the scene. Once we made this alignment, this generates a 3D frustum, which is practically the location in 3D space where we know that our object needs to lie. There's a few tricks that needs to be taken into account during this process. One is the scale. So typically, because the method that we use to generate our 3D model is trained to generate multi-view images from a fixed camera parameters, then we can get typically scale issues. And so we have to, let's say, estimate the scale of the object with respect to the scene. And we do this by optimizing the scale via mean square error with respect to the original image with a cap, or the object that we want to insert. The other thing that we need to take into account, this is a little bit more tricky, I think, is actually the density. So the density of the two nerve models, so the object that we generated and the original scene, they're actually different and they can't just be merged via simple averaging. If you do simple averaging, then this leads to very degraded results in terms of the rendering, as we can see in these images. And so what we need to do is actually rescale the density to retrain the appropriate color. And this is actually a procedure that needs to be done for every single ray. And so we have for every single ray to define and determine through these formulas the right density. And that gives basically the appropriate rendering properties to our added object. I just jumped to the results. So this is practically one of the examples. So we take the prompt and then we generate the object inserted in the scene, and then we can practically generate this sort of like trajectories around the scene with the added object. I'll show you some more examples. Here you can see on the left-hand side the original image, the original rendering of the nerve scene, then in the middle the edited one, and also the depth that we get in terms of the edited one. So on top we have added this panettone to the scene, and on the bottom we have instead a mag next to the caterpillar. These are another set of examples, qualitative in terms of outdoor scenes. So on top we can see one of the standard nerve scenes where we also had a mag on the table. And here in the middle, in the bottom, instead we see an example where we had a butterfly in the center of the scene, and then we create a trajectory around it, still one of these nerve scenes. This is also like a qualitative comparison with instruct nerve to nerve, where we see, for example, the difference that we can get in terms of spatialized, or let's say, localized editing, and in terms also of the consistency of the results in terms of multi-view. There's, of course, a lot of, let's say, limitations in this work. And so one of them is that it's still hard to handle very complex lighting effects, and it still suffer of biases that are included in the diffusion priors. And so these are aspects that we're trying to improve with future work. Great. And so the third and last part that I wanted to briefly introduce to you is actually some work that goes on top of, let's say, actually a direction that we've been following for quite a few years, which is the idea of using scene graphs as a very powerful way to represent a 3D scene. In this case, let's say, looking at ways that we can generate 3D scenes, there's actually many methods that do it, for example, iteratively by going into a database of 3D objects and then using a network to, in this case, autoregressively go and pick the next best 3D object that needs to be placed given a layout and a set of predetermined objects. And so in this case, we start from the layout, and the network will, for example, pick the best 3D object, and then based on these 3D objects, just fit the next one. And so these type of methods are quite interesting in terms of the results that they can get. They're very realistic, but of course they leverage objects that are already predetermined in a database, as well as they can lack a little bit the relationship that needs to be taken into account between objects in the scene. And so in order to increase the controllability, we believe that scene graphs are a very good tool to generate also 3D scenes. So that's something that we've been now exploring for quite some time. So in order to, let's say, describe how we can generate scenes with scene graphs, I want to briefly define what a scene graph is, and in particular 3D scene graph. So we started with this definition with the work we did in 2020, where we took actually the scene graph approach and definitions that were typically used for images and brought them to the 3D field. And in this case, we defined scene graphs for 3D scenes as a set of nodes that typically represent entity in the scenes, typically objects, but also structural elements of the scenes, and then relationship that would be generally encoding different types of properties between two objects or two entities in the scene, such as, for example, their geometric relation, their similarity in terms of texture, material attributes, and so on and so forth. And so scene graphs are actually powerful tools for both doing inference and generation of data. And for inference, we've been using them to, for example, given a set of 3D scans of scenes, or given a set of sequences, RGBD sequences, or RGB sequences of scene, to actually extract the 3D scene graphs out of this. But in this case, we're actually interested in kind of the opposite process, which is I give you a scene graph and I want to generate a scene, and the 3D scene needs to respect the entities and the nodes and the relationships of the graph that I provide you as input. This is one of the works that we presented in 2021. And so the idea is that if you provide a scene graph that uses a condition, then in addition to generating a scene, then you can also, let's say, play around with the scene graph in order to apply manipulation. So you can, for example, start replacing the nodes or replacing the relationship, and you will generate different types of scenes where you tend to, let's say, apply this type of editing directly on the generated scene. In this case, the way to develop this approach was actually an autoencoder-like network, where we start from a set of, let's say, shapes as input that get encoded into a shape encoder. And then on the bottom, you can see a set of layouts that represent the 3D bounding box in the scene of that object with a class associated as a label. They both get encoded, and then we have a shared encoder, which eventually is going to be a GCN, a graph convolutional network, which is what creates a shared embedding. So eventually, you can really get a scene graph as the embedding. And I think this is a very powerful property, because then you have an embedding that you can really play with. So you can start manipulating your latent variables, because they're going to be entities and relationship edges of this graph. And so you can also do this type of manipulation in the latent space. And then you have to decode everything, right? So you have, again, two decoders. One decoder that decodes the 3D layout in terms of the bounding boxes, 3D bounding boxes in the scene. And then for each of these bounding boxes, we need to fill them in with a shape. And so we have a shape decoder that decodes the particular shapes that needs to be filled. It needs to fill in each of the 3D bounding boxes. And so in this case, we really generate shapes that are not taken from a 3D database, but can be generated based on also the relationship that are imposed by our graph. The next work, which is actually what I wanted to present a little bit more in detail today, is a work that we published last year at NeurIPS. and it's called common scenes, and kind of improve and builds on top of this idea that I just explained by using or trying to exploit the power of diffusion models. And so the idea is very similar in terms of the overarching, let's say, structure. And so we have a scene graph that is used as an input to condition the process. We have an encoder that's eventually also modeled with a scene graph as part of the latent embedding, let's say, of the scene. And then we have this type of decoder that is split into two branches, a shape branch and a layout branch. And so the main difference is that in the shape branch, we actually want to use a diffusion model to generate better shapes, conditioned also by the relationships of the graph. The first step that we do is to pre-process each of the nodes and relationship that we have from the scene graph to go from a standard scene graph, which is what I defined before, to a so-called contextual graph. A contextual graph, you have to think about it as an augmented scene graph, where in addition to the embedding that we have for each of the nodes and entities, we actually add a clip text embedding. So that practically takes the label of the entities of each of the nodes and uses like a clip embedding to leverage more information about the object properties, and also encode the 3D scene layout as a set of parameterized 3D bounding boxes. So imagine augmented, let's say, the nodes and relationship with this type of small feature vectors. And so this, let's say, contextual graph is now ready to be encoded in our encoder. And so for the encoder, we eventually, again, use a GCN, a graph convolutional network. And we use it in a way that the features that are learned in this latent space are actually to be interpreted as a VAE. And so because it's a variational encoder, then you can think about it as a distribution represented by each of these features. And then you can sample from the nodes and from the relationship in order to generate, based on the same starting scene graph, different types of 3D scenes. Now, the layout branch is very similar to what I explained before. So we typically decode from the nodes of the graph a layout, so a set of 3D bounding boxes that are in a relative position to each other. And this is simply done with an MLP. So with a simple MLP, we decode this and use this type of loss for the layout, which is nothing but something that penalizes the bounding box size, the bounding box location, and the angular rotation of the bounding box. So very, very simple. The more interesting part is on the shape branch. As I said before, here we wanted to explore the idea of using diffusion, and in particular, we use a 3D unit-based diffusion. So it's really like a diffusion model in 3D space, where the underlying representation for our data is a sign distance function. For the sign distance function, we practically encode it into a latent space, and through the latent diffusion model, we practically tend to denoise basically this latent representation of the SDF. One interesting thing to note here is that we are now conditioning, see it here, we wanted to condition the diffusion process, the denoising process, with an embedding of the relationships from the graph. And so this is where the graph, let's say, magically comes in the process by taking the edges between the nodes, taking their embeddings from the GCN, what we've seen before, and using that as condition. We want to make sure that the shape that we're generating gets influenced by the nearby nodes in the graph. So those nodes in the graph, there's some sort of relationship, like as I said before, they have the same shape, or they have the same label, or they have the same semantics. They will condition so that, for example, if you need to generate a set of chairs around the table, you have more chances that these chairs are going to be all the same rather than individually and independently developed, right, decoded. I think that's mostly it about this slide. And so jumping to some of the results, you can see some examples starting from this type of graphs, how the 3D scene is generated. Again, these are the individual shapes decoded for each of the nodes in the graph and placed into the 3D bounding boxes generated by the 3D layout. These are some other examples of scenes We also have in the paper several comparisons that we made. One is a very important aspect, which is the realism, how realistic are the generated scenes. So in this case, we use two metrics, FID and KID, in terms of that measures, let's say, some sort of realism of the scene with respect to the state of the art, and we got particularly improved results also through the 3D SLN and graph-to-box methods that I just mentioned before. Diversity is instead a study that wants to show how different 3D shapes can be generated by seeding, so by sampling differently the variational autoencoder that we have at the level of the embedding based on a GCN. So you can see here how the same scene graph can actually lead to different types of 3D shapes in the scene that are all semantically consistent with each other. And finally, this is also something that can be used in terms of manipulation of the scene graph. So we can actually control the scene by manipulating, for example, changing the nodes, the labels of the nodes. We can, for example, change the attributes, make, for example, the nightstand taller or make the TV stand bigger. We have let's say, more recent method has been just published in arXiv very recently that tends to further improve this work. If you're interested, you can have a look at that. And in this case, we can also generate texture for the 3D scenes. Actually, this improves a lot of, let's say, the aspect related to the realism of the scene, because we can now also use the prompt to generate, let's say, stylistic attributes that can be applied on the scene. This is actually all. I want to thank you for the attention. I think we have still a couple of minutes in case of any questions, and thanks for listening until here.
Thank you, Federico, for this great talk. I mean, we have a couple of minutes for questions, and let me maybe start with one. How far are we away from having this, like, very efficiently, like generating 3D like for AR applications? Like, I'm wearing an AR glasses, my son is wearing some, and I would like to, generate a unicorn running on our table. How far are we away from something that is like fast?
Yeah, so in the methods that I presented today, in particular text-to-mesh, we didn't really focus on the efficiency aspect. So this is actually a method that's definitely not designed to be, for example, real time or to generate things efficiently. But there are now several, let's say, approaches that have made like a lot of progress in that sense. And for example, recently, I think Andrea also mentioned some of these works that tend to, for example, rely on the idea of generating consider that once you generate, for example, a frame sequence or a video sequence, the consistency, underlying geometry consistency might be at stake. It really relies on how well the foundational model that you use for generating video sequences is able actually to reason intrinsically on 3D properties. But that's definitely one of the ways, a very promising way to generate things much faster, let's say, much more efficiently.
Yes, I forgot to say, our method really takes 1 minute, just as a reference. That's what you get, 30 seconds for a preview and another 30 with text.
And how far are we away from getting this on device? Like, yeah, far.
It's not okay. No, it is. No, 2 more years, months.
But it's
I think there's already methods that can be, let's say, used on device, but they would definitely provide let's say you'll notice a significant deterioration of the results. For example, there's this nice tool that Luma AI put, let's say, also on the web, that can really provide very, very quickly assets. It's not on mobile, but it's very fast. You can also see that if you really request results in the order of seconds, then you have a strong degradation of the results. So you get, for example, 3D meshes that are incomplete or the missing parts. other inconsistencies. And I would expect that once you start putting this on mobile right now, you get also similar results. So it eventually also the question is what do you want to get? You want something fast on mobile and extremely accurate, right? And so if that's your goal yet, then yes, you're gonna need to wait still a few more years.
Actually, I did have a question. So, I was very interested in the paper where you add the objects to the scene. So how can you make, say, the lighting consistent, for example? So you have shadow, cast shadow, for instance, or in general, you want the illumination to be compatible with what you get in your scene. Is there something you can do yet?
Yeah, so that's one of the aspects that I mentioned in terms of limitations / future work. So in this case, we don't really take that specifically or explicitly into account. And so let's say in case, for example, you're going to place an object on a table, and on this table there's a ray of light that just shades some part of the table, and that's where you're going to put the object. That's something that would be generate, let's say, inconsistencies. I think there are ways that you can actually deal with that, and so that's some interesting, let's say, next step for the work. Yeah.
Hi, great talk. I wanted to ask you, for example, combine aspects of the first and the third. So, like, how do you think, how far are we from generating entire game scenes or maps?
Again, I think we are still scratching a bit the surface of this type of methods. One of the main limitations is also that it's really hard to talk, for example, about 3D foundation models, right? That can be, let's say, for example, a nice backbone for generating this type of assets, and that you can also then try to optimize in order to generate quickly 3D scenes or 3D assets together. Then, of course, it depends also on the type of application that you have in mind, in the sense that many type of also gaming use cases can be simplified by generating most of your data in a 2D manner, right? You don't really need, for example, 3D meshes for certain gaming applications, or not necessarily, right? And so these are also tricks that then you can use to speed up a little bit your work. Yeah.
Good. We are perfectly on time. So thanks again, Federico.